Half the moon is missing from our sky, a locked hemisphere we never see from Earth, and when spacecraft finally turned the cameras around, it wasn't the moon we recognised, scarred, jagged, and strangely silent. The maps didn't match, the terrain didn't make sense, and the story kept changing. So what's really on the far side of the moon, and why does it feel like someone didn't want us looking too closely? For all our talk of conquering space, half the moon is still a locked door. When humanity finally looked, what stared back did not resemble the moon we thought we knew. Every night the moon turns one familiar face toward Earth, steady as a promise, and old as legend. Yet beyond that bright curve lies a hemisphere no telescope can watch directly, an entire world hidden in plain sight. For centuries, that unseen terrain became a canvas for certainty, fear, and the most durable rumour of all. Then the space age arrived, and the far side stopped being poetry and became evidence, grainy at first, disputed, and impossible to ignore. The images were imperfect, but the shock was clean. The far side was not simply the near side under different light. It looked older, brighter, more scarred, less a portrait and more a record of violence. And in the gaps between what was captured and what was withheld, suspicion found room to breathe. So what is actually on the far side of the moon, and why is it so different from what we see? Is the asymmetry a natural consequence of heat, crust, and ancient impacts, or a sign that something was missed, filtered, or quietly managed? To answer, we have to follow the moon's own rules, beginning with the slow mechanics that keep one face turned toward us forever. We will trace how the first far-side photographs were made, and why their flaws mattered almost as much as their facts. We will step across a boundary where dark plains give way to rugged highlands, and where crater fields behave like a clock that only runs in reverse. We will read the far side's biggest basins as if they are fingerprints from the solar system's earliest chaos, left untouched because resurfacing never erased them. We will compare maps of minerals and elements that look like coded messages until you learn the physics that writes them. And we will listen, because the far side is not only hidden from our eyes. Behind the moon, Earth's radio noise falls away, leaving a rare, guarded quiet that can make any stray signal feel like a confession. Blackouts happen there by geometry, not by intention, but the effect is the same. Long minutes where nothing returns, and imagination fills the silence. Landing on that hemisphere raises the stakes further, because on the far side there is no direct lifeline home. Every command must arc through a relay, every image must survive compression, calibration, and delay, and every missing frame becomes a story someone will tell for you. In the cold shadows near the poles, even the dust and darkness can hold resources, real ones, measurable ones, that sharpen the question of who gets to know first. This film does not ask you to choose between wonder and doubt. It asks what happens when incomplete data meets secrecy, when genuine anomalies meet human pattern hunger, and when a place we cannot see becomes a stage for our deepest suspicions. The far side may not contain a single hidden secret. It may contain something stranger and more consequential, a preserved half-world still carrying the earliest chapters of planetary history, and perhaps the quietest listening post we can build for the universe's first light. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 10 chapters, we move from the physics of the moon's locked rotation to the first blurred photographs, the two-faced geology, and the far side's unnerving radio quiet. And when the cover-up claim is finally put on trial, the evidence will lead somewhere deeper than rumour, toward origins, silence, and the next frontier of discovery. We look up and think we know the moon, because one face always looks back, steady and familiar. Night after night, the same pattern hangs above rooftops and treetops, and it feels complete. Yet half of that world stays turned away, not by darkness, but by motion, an elegant constraint written into the sky. The phrase dark side is the first misunderstanding we have to clear away, because it sounds like a permanent shadow. The far side is not permanently dark, and it is not a hidden cavern. It is simply the hemisphere that never faces Earth, even though it still cycles through day and night. When the sun rises there, it rises for 2 Earth weeks at a time, then sets for 2 more. From orbit, that rhythm is stark and physical. Sunlight crawls across crater rims, pours into basins, and then drains away, leaving long razor-edged shadows. The far side has noon and midnight like anywhere else on the moon, but it has no Earth in its sky. That absence is part of the spell, an entire hemisphere without the blue anchor we take for granted. The reason we never see it directly is tidal locking, a slow gravitational negotiation written into the moon's orbit. Earth's gravity raised tidal bulges in the young moon, and internal friction bled away rotation. Over time, the moon's spin matched its orbital period, and the same side stayed pointed home. This is not a switch that flipped in an instant, but a gradual settling, like a spinning top losing energy. In the early solar system, the moon likely rotated faster, while its interior was warmer and more deformable. As Earth tugged on those bulges, the moon's rotation was braked, and heat was dissipated inside the rock. That heat was not dramatic like a volcano, but it mattered. Friction can reshape a world's long-term behavior. The end state is a minimum energy configuration, and nature tends to prefer those. Synchronous rotation sounds like a trick, but it is a stable outcome of physics, especially for close satellite systems. The moon rotates once for every trip around Earth, about 27.3 days. From the ground, that matching rhythm makes the near side seem fixed, while the far side remains out of view. It is the same principle that keeps many moons in the solar system showing one face to their planets. If you could stand far above the lunar North Pole and watch for a month, the geometry becomes obvious. The moon turns, but it turns at the same rate it travels, so the same hemisphere keeps leading with familiar landmarks. The bright splash of Tycho, the dark oval of Mare Imbrium, the subtle grey seas, these become a repeated portrait. The far side, meanwhile, keeps its own portrait turned outward into space. Even that never has a footnote that matters for the story, because the lock is not perfectly rigid. Because the moon's orbit is slightly tilted and slightly elliptical, we get libration. Over a month, Earthbound observers can peek a little around the edges, seeing roughly 59% in total. The moon seems to nod and sway, as if it is trying, almost, to show us more. Libration comes in several flavours, and each adds a small, measurable drift. The elliptical orbit makes the moon speed up and slow down, while its rotation stays nearly constant, so we glimpse a bit more east and west. The tilt of the orbit lets us see slightly over the north and south poles at different times. Even Earth's own rotation changes the viewing angle across a night, adding a subtle parallax that careful observers can exploit. For most of human history, that remaining 41% was more than unseen. It was untestable, unreachable, and therefore endlessly describable without consequence. The far side became a blank page where myths, fears, and ambitions could be written, erased, and rewritten. When a place cannot contradict you, imagination gains an unfair advantage. Cultures built lunar stories from the face they could see, then filled the missing half with invention. Some imagined a mirror world, others a realm of spirits, others a place of perfect symmetry. The absence of evidence did not slow the narratives, it accelerated them, because mystery is a kind of fuel. The moon's visible markings became a template, and the unseen half became a projection screen. Even in more scientific eras, the temptation to assume symmetry lingered. If the near side had dark planes, then perhaps the far side did too, hidden only by geometry. If the moon was one object, why would it have two different faces? Before spacecraft, these were reasonable guesses, because nature often repeats patterns, and the data simply wasn't there. Modern rumour did not replace ancient myth, it upgraded it with new vocabulary. In the 20th century, secrecy and technology made the far side feel like a classified location. If you could not verify it yourself, someone else could claim they had. The language shifted from spirits and omens to bases and transmissions, but the psychological structure stayed familiar. That is why the far side became a perfect canvas for cover-up thinking. A place you cannot see invites the idea that you are not allowed to see. Orbital mechanics created the blind spot, and human psychology turned it into a motive. The mind treats missing information as a pattern to complete, and suspicion supplies the missing pieces. We should name the stakes plainly, because they are not only emotional. A hemisphere of our nearest neighbour was unknown terrain, and unknown terrain attracts power. It attracts military interest, scientific competition, and the temptation to control the story. During the Cold War, even the vocabulary of space exploration carried strategic weight. The early space age sharpened that temptation into a geopolitical edge. Rockets could finally reach the moon, and cameras could finally look back. The far side became a target for firsts, and first became tools of national prestige. A single photograph could signal capability, and capability could imply deterrence. In that environment, the line between what is hidden and what is merely hard to measure gets blurry. Some information was genuinely classified for strategic reasons, especially when rockets and guidance systems overlapped with weapons development. Some was simply incomplete, noisy, or misunderstood in the rush to interpret it. Early signals were weak, early images were crude, and early conclusions were often provisional. This documentary treats those categories as separate questions, even when they overlap. What is physically hidden by geometry is one problem. What is hidden by secrecy, miscommunication, or selective release is another problem. If we mix them together, we end up arguing about feelings instead of evidence. To investigate a cover-up claim, we first need a baseline of what should be expected given what physics allows. If the moon were a simple, uniform sphere, the far side might resemble the near side. If it did not, then difference itself would demand explanation, even without conspiracy. The key is to ask what a natural moon should look like before we decide what looks unnatural. The first surprise is that the far side is not just unseen, it is different. The near side shows broad dark plains called maria, ancient basalt floods that filled giant basins. The far side is dominated by brighter, heavily cratered highlands, with far fewer maria. The contrast is not subtle when you finally see it, because the textures change as well as the colours. On the near side, the maria look like frozen ink spilled across stone, smooth at large scales and dark against the pale crust. Their edges curve around impact basins, and their surfaces are relatively flat, interrupted by wrinkle ridges and scattered craters. On the far side, the landscape is more like hammered metal, densely pocked, bright and jagged, with overlapping scars that rarely give way to wide, dark plains. That contrast is visible even in the simplest summary of lunar maps. One face is smoother and darker in large patches, the other is rougher and brighter overall. The moon we thought we knew from Earth is not the whole moon, it is the unusual half. The part we grew up with is, in a geological sense, the exception. The difference goes deeper than appearance, and it is not a minor detail. Measurements indicate the far side crust is thicker on average than the near side crust. A thicker crust can suppress volcanic flooding, which helps explain why maria are scarce. If the crust is a lid, then thickness changes how easily the interior can vent its heat. Crustal thickness is not guessed from photographs, but inferred from gravity and topography. Orbiters track tiny changes in spacecraft motion as they pass over mass concentrations, revealing where rock is denser or lighter beneath the surface. Combine that with laser altimetry, and you can estimate how the crust flexes and how thick it must be. The result is a moon with hemispheric asymmetry that shows up in numbers, not just in pictures. Chemical and thermal histories also appear to diverge between hemispheres. The near side is enriched in certain heat-producing elements compared to the far side. That enrichment affects how long rock stays warm enough to melt, and where lava can reach the surface. In plain terms, one side had more internal battery power to keep volcanism going. Those heat-producing elements include potassium, rare earth elements, and phosphorus, often grouped as creep in lunar science. They are not magical substances, but residues of early differentiation, concentrated as the moon's magma ocean cooled and minerals separated. Where those elements accumulated, they would have increased radiogenic heating over time. That extra heat can thin the lithosphere, promote melting, and make basalt eruptions more likely. So the real mystery is not only why we never see the far side from Earth. The deeper mystery is why the moon has two faces with different geological stories. That question is scientific, but it has always been vulnerable to sensational answers. When a world looks asymmetric, people naturally ask whether something acted on it or happened to it. Before we chase anomalies, we need to understand why the moon matters as a record of deep time. Earth is geologically active, and it erases much of its early history through plate tectonics and weathering. The moon is quieter, and it preserves scars that Earth has lost. Its surface is not timeless, but it is less frequently rewritten. Every crater is a timestamp of impacts that shaped the early solar system, because crater density can be used as a rough clock. Every basalt plain is evidence of internal heat and ancient volcanism. In that sense, the moon is an archive, and its pages were written when the planets were still settling. When we read those pages carefully, we learn about Earth's own missing chapters. The far side may be an even more pristine archive in key ways. With fewer basalt floods, more of its ancient crust remains exposed. That makes it a valuable place to read early bombardment history and to test models of how the moon formed and cooled. If you want to study the oldest surviving surfaces, you look where resurfacing was least common. There's also a cosmology angle that is less familiar, but increasingly important. The far side is shielded from Earth's radio noise, creating a uniquely quiet environment. That quiet could help future instruments listen for faint signals from the early universe. Earth is a loud transmitter, and our atmosphere blocks or distorts many low-frequency radio waves. From the far side, the moon itself becomes a physical barrier, blocking the chatter of human technology. Radio telescopes there could search for the red-shifted hydrogen signal from the cosmic dawn, when the first stars switched on. They could also monitor space weather and solar bursts with less interference. The far side is not just hidden from us, it is sheltered from us. A place can be valuable without being mysterious, and mysterious without being valuable. The far side is both, which is why it keeps pulling attention back. It is close enough to reach, distant enough to conceal, and strange enough to provoke questions. The same geometry that hides it also frames it as a prize. Still, the cover-up narrative persists because it feeds on real asymmetries in knowledge, not only on fantasy. For centuries, no one had images, samples, or direct measurements from the far side. When information finally arrived, it arrived through institutions that did not always share everything. Even honest scientific uncertainty can look like evasiveness when the audience expects certainty. The first time humanity truly saw the far side, it was not through a telescope. It was through a spacecraft, and that shift matters. Spacecraft data is mediated by hardware, processing, and interpretation, which means trust becomes part of the equation. A camera is not an eye, and a transmission is not the scene itself. That does not mean the data is fake, but it does mean the public rarely sees raw reality. Most people see curated images, selected maps, and simplified explanations. In a climate of suspicion, curation can look like concealment. The question becomes not only what was seen, but who chose what to show. It also matters that early space imaging had constraints that modern viewers forget. Film had to be scanned, signals had to be reconstructed, and contrast had to be adjusted to reveal detail. A cratered surface can look flat without the right lighting, and a shadow can look like a void without context. When you add compression artifacts and partial coverage, ambiguity is almost guaranteed. This chapter sets the ground rules for the investigation that follows. We will separate the moon's physical constraints from human choices about information. We will track how each new dataset changed the story, and how gaps in understanding became fuel. We will also ask a harder question. What kind of evidence would actually change a skeptic's mind? The structure is straightforward, because the subject is not. We begin with myths and assumptions that grew in the centuries of ignorance. Then we move to the first images that shattered symmetry and created new puzzles. Once the far side stopped being imaginary, it became something more demanding, a real landscape with measurable properties. From there, we follow the anomalies that people point to when they claim something is being hidden. We examine what those anomalies actually are in the data and what they are not. We compare competing explanations from mundane to exotic, and we keep score. The goal is not to mock belief, but to test it against what the moon will allow. We also make room for what remains unresolved, because uncertainty is not evidence of deception. Some questions persist because the moon is complex and our measurements are limited. Some persist because the best tests require missions that are difficult and expensive. A lack of answers can be a budget problem, a technology problem, or simply a patience problem. The far side is not a single secret waiting to be revealed. It is a landscape, a history, and a set of measurements that sometimes disagree. The cover-up idea is one hypothesis among many, and it must compete with physics, geology, and engineering. If it cannot explain the data better than natural processes, it does not earn the spotlight, but the hook remains because the first look did not match expectations. If the moon formed from the same event, why does one hemisphere look so different? If impacts and volcanism shaped both sides, why did they leave such uneven signatures? When nature breaks symmetry, it is often telling you about a hidden variable. Those questions do not require hidden bases or forbidden photographs to be compelling. They require careful attention to orbital mechanics, thermal evolution, and the messy randomness of impacts. They also require us to examine how institutions communicate uncertainty to the public. When officials simplify, do they clarify, or do they accidentally invite mistrust? So we start where the misunderstanding begins, with the phrase itself. There is no eternal darkness on the far side, only a locked rotation that keeps it turned away. The darkness is in our knowledge, and knowledge can change. The moon is not hiding, but it is also not obligated to be simple. In the next chapter, we follow the moment that ignorance ended. We trace the first spacecraft that slipped behind the moon and sent back proof of a different world. The mystery shifts from what we cannot see to what we did see and could not explain. And once you have seen it, the far side stops being a metaphor and becomes an argument with evidence. For centuries, the far side was a blank, so symmetry felt like common sense in the dark. The near side showed dark Maria and bright highlands, and many assumed the pattern repeated beyond view. In early sketches and popular astronomy books, the moon was drawn like a coin, two matching faces merely turned away. That assumption survived because telescopes could not break the lock of tidal rotation, a slow gravitational handshake with Earth. The moon spins once per orbit, so the same hemisphere keeps facing us, night after night, century after century. Libration offered edge glimpses, a gentle rocking caused by orbital eccentricity and tilt, but it never delivered the missing hemisphere as evidence. Even at its best, libration revealed only slivers, foreshortened, shadowed, and easy to misread. Then the space age turned geometry into a solvable engineering problem. To see the far side, a probe only had to survive the trip, point a camera, and talk back. That only hid the real challenge. Navigation, power, thermal control, and radio links had to work while Earth disappeared behind the moon. In the late 1950s, the Soviet Union pushed firsts that were also signals of capability. Each launch implied guidance, tracking, and rockets that blurred civilian exploration with military reach. The same mathematics that could place a probe near the moon could also in principle deliver a warhead across continents, and everyone understood that subtext. Lunar 1 missed the moon but proved a trajectory could reach lunar distance, a feat of timing and propulsion rather than luck. It flew past into solar orbit, carrying instruments that tasted the space between worlds and confirmed the solar wind. Lunar 2 impacted the surface and made the moon a destination, not a metaphor. The crash itself was the message. Human engineering could touch another world. The real turning point arrived in October 1959 with Lunar 3. It swung behind the moon, photographed the unseen hemisphere, then returned the images by radio. The flight path used the moon's gravity like a sling, an early demonstration of what later became routine, but then felt like wizardry. This was not digital imaging, and it was not a clean broadcast, even by the standards of the day. The camera exposed film on board, developed it inside the spacecraft, then scanned it line by line. In a small pressurized compartment, chemicals had to behave predictably while temperatures swung and vibrations lingered from launch. Every step imposed loss, noise, and room for interpretation. Film grain, uneven development, and scanning artifacts all competed with real lunar detail. The first far-side photographs were data, but they were also an argument about what counted as a picture. When a crater rim is only a few pixels wide, where does geology end and imagination begin? The Soviet release was partial and processed because it had to be. The transmission bandwidth was limited, the signal was weak, and the ground reconstruction was imperfect. Engineers had to choose what to prioritize: contrast, legibility, or completeness, because early telemetry could not deliver everything at once. Even so, the shock was immediate. The far side did not resemble the familiar face that stared down at Earth's nights. Viewers expected a mirrored moon, yet the first frame suggested a different personality, less smooth, less dark, and more relentlessly scarred. Instead of broad, dark seas, the first images showed a bright, heavily cratered terrain. Scientists expected some differences, but not a hemisphere that looked older and rougher overall. The tonal contrast was striking in black and white. Few large dark patches, many pale highlands, and crater rims stacked like overlapping rings. The missing Maria became the first big puzzle that ordinary viewers could grasp. If the near side had dark plains, why did the far side have so few? The question sounded simple, but it pointed toward deep interior processes: heat, chemistry, and the thickness of rock above molten sources. Maria are basalt floods that filled low basins long after the biggest impacts. They are not water seas, but they behave like liquids in the way they level terrain. Basaltic lava is runny compared with the stickier lavas of many volcanoes on Earth, so it can spread wide before it cools and freezes. On the near side, giant basins like Imbrium and Serenitatis became containers for later lava. The dark colour reflects basalt composition and the way it weathers in vacuum. Over time, micrometeorite impacts and solar particles darken the surface, turning basalt plains into the familiar charcoal patches visible to the naked eye. On the far side, the early images suggested fewer large basalt plains. That implied either fewer suitable basins, less lava, or a crust that resisted eruption. Each possibility carried different consequences, and none could be confirmed from a single blurred mosaic. Scientists began framing the problem as a chain of causes. Impacts create basins, basins create lowlands, lowlands invite lava, and lava erases older craters. If one link in that chain differs by hemisphere, the surface history diverges. The far side seemed to preserve impact scars that the near side had partly buried, as if one half kept its ancient skin. Crater density offered a way to turn appearance into time. On airless worlds, older surfaces accumulate more impacts and become more densely cratered. Without wind, rain, or plate tectonics, a crater can persist for billions of years, slowly softened only by later impacts and the steady gardening of regolith. This is not a perfect clock, because impact rates change over billions of years. The early solar system was more violent, and the flux of debris declined as orbits cleared. Still, relative dating works because resurfacing resets the count like repainting a wall. When lava floods a plain, it buries older craters, and the crater count starts over on a fresh surface. A smooth basalt plain with few craters is usually younger than a battered highland. A terrain with overlapping craters and few lava fills is usually older. Even in noisy images, the eye can sense the difference. Smooth expanses read as calm, while crater-saturated terrain reads as ancient turmoil. So the first far-side photographs hinted at an older average surface age. They suggested less resurfacing, fewer lava floods, and a crust that stayed exposed. In other words, the far side looked like it had been spared the moon's later volcanic phase, or it had been physically unable to participate. That conclusion did not require conspiracy, only geology and statistics. Yet it landed in a world trained to read space news as propaganda and threat. In 1959, every radio transmission from deep space carried a second shadow. What else could these systems do, and what else might they be hiding? The Cold War shaped how the first images were received. The same tracking networks that listened for lunar probes also listened for missiles and bombers. Antenna arrays, timing standards, and signal processing were dual-use tools, and both superpowers guarded them with instinctive caution. Both superpowers had reasons to control what they revealed about sensors and coverage. Even honest limits could be described as secrecy, because secrecy was normal. A missing frame could be an engineering failure, but it could also look like deliberate omission when trust was already thin. Lunar 3 did not map the whole hemisphere. It returned a partial view at low resolution, with large gaps and uncertain lighting that hid subtle features. The sun angle mattered. Long shadows could exaggerate relief while high sun could wash out texture and erase the faint rims of older craters. That incompleteness created two stories at once. Scientists saw a first data set that demanded follow-up, while skeptics saw a first release that could be curated. When the boundary between unseen and withheld is invisible, suspicion fills the space. The pictures did not show obvious structures that screamed artificial origin. They also did not show enough detail to rule out claims that something might be missing. A blurred ridge could be a mountain chain, a scan line, or a processing artifact. Each possibility sounded plausible to different audiences. This is the tension that will repeat throughout the documentary. Early data arrives incomplete, institutions summarize it, and the gap becomes a breeding ground for suspicion. The public rarely sees raw telemetry, so it must trust intermediaries, and trust was the scarcest resource of the era. In the early 1960s, the United States raced to catch up in lunar reconnaissance. Ranger missions aimed to return close-up images before impact, proving camera and telemetry chains. They were also a rehearsal for Apollo. If you could not transmit pictures reliably, you could not navigate, land, or survive. Ranger 7 in 1964 delivered thousands of near-side images in the final minutes. It showed that the moon's surface was not smooth, and it validated high-rate transmission. Craters appeared within craters, boulders cast sharp shadows, and the romantic idea of a gentle lunar plain collapsed into hard geology. Those Ranger successes mattered for the far side indirectly. They proved that higher resolution was possible, and that future orbiters could map systematically. They also taught engineers how to stabilize cameras, manage exposure, and keep radios locked while a spacecraft fell at kilometers per second. The next leap came with lunar orbiter missions in 1966 and 1967. Their job was practical and political, to scout landing sites for Apollo and demonstrate mastery. Orbiters could do what flybys could not, return again and again, building coverage until the unknown became an atlas. Lunar Orbiter used film too because film still beat early digital sensors. It developed film on board, scanned it, and sent it to Earth as analog signals. The process was ingenious and delicate. Rollers, tanks, and scanners operating in vacuum, as if a small photolab had been sealed inside a metal drum. That method produced sharp images but also artifacts. Dust, scratches, scanning lines, and contrast choices could create patterns that looked meaningful to anxious eyes. A bright streak might be a film defect, yet in a world primed for secrets, defects can masquerade as censored marks. Orbiter coverage expanded beyond the near side because orbit does not care about human convenience. Over time, the far side entered the archive as strips and mosaics. In mission control rooms, technicians assembled these strips like puzzle pieces, aligning craters, matching shadows, and slowly replacing rumour with cartography. Yet public attention stayed focused on Apollo and the near side. The far side remained remote in the popular imagination, because no crew would land there in that era. Even the phrase dark side lingered, a poetic misnomer that made the hemisphere feel forbidden rather than simply unseen. While the United States mapped, the Soviet Union continued automated lunar work. Zond circumlunar flights carried cameras and returned photographs, sometimes with selective publication. Each new image release arrived with the same ambiguity. Science framed as achievement, and achievement framed as strategic theatre. Each new release sharpened the missing seas puzzle. The far side was not just slightly different, it was systematically lacking the dark basalt expanses that define the near side. The contrast became more than aesthetic. It became a clue that the moon's interior had not cooled and evolved uniformly. Scientists refined the basalt story to explain the contrast. Basalt flooding requires melt, pathways through crust, and basins low enough to pool lava. On the moon, melt is produced by internal heat and radioactive decay, then guided by fractures and weaknesses left by impacts. If the far side crust is thicker, magma has a harder time breaking through. If the near side has more heat-producing elements, it stays warmer longer and melts more. These ideas were not fully proven by the first photographs, but the photos made them necessary. A symmetric moon no longer fit the simplest reading of the evidence, and symmetry stopped being the default assumption. Impact basin formation also entered the explanation. Large impacts excavate deep cavities and thin the crust locally, making later volcanism more likely. A basin is not only a scar on the surface, it is a structural wound that can focus stress, open fractures, and create a low place where lava can spread. If the near side received more basin-forming impacts, it would gain more volcanic containers. If the far side's basins were fewer or less favourable, Maria would be scarce. The first images could not count basins reliably, because resolution was too low. But they could show the overall texture, and the texture looked like old highlands, pale, crowded, and complex. Crater density became the public-facing shorthand for age. More craters meant older, and the far side looked like it had been left out in the rain longer. In photographs, the near side's Maria read as open spaces, while the far side read as a surface with no empty pages. That shorthand is useful but dangerous. A surface can be old because it formed early, or because it avoided later resurfacing that would erase its scars. So the far side might not be older rock everywhere. It might be a surface that stayed exposed while the near side was repaved by basalt and ejecta blankets, layer after layer. This distinction matters for the cover-up narrative. A different face does not imply an unnatural cause, but it does imply a missing variable in lunar history. If nature can produce such a stark hemispheric contrast, what else might we be misreading when we assume uniformity? As the mapping improved, another pattern emerged. The far side's highlands seemed more continuous, while the near side's Maria broke the crust into familiar dark patches. The moon we grew up with began to look like the odd half. The far side began to look like the default state of an airless body battered for eons, an ancient crust heavily cratered and only lightly modified. Still, the first far side photographs carried an unavoidable ambiguity. They were the product of limited telemetry, limited coverage, and political incentives to control messaging. Even the choice of which frames to publish first could shape perception, because first impressions harden quickly. Selective release did not have to mean deception to feel like it. When only a few frames are shown, audiences assume unseen frames exist and might contradict the story. A scientist may think in terms of signal-to-noise and partial data sets, but a suspicious viewer thinks in terms of missing evidence. Classification also hovered in the background. Tracking accuracy, antenna sensitivity, and image processing pipelines were strategic assets, and governments protected assets. The public rarely heard about these technical constraints, so silence sounded like evasion, even when it was simply standard security practice. That protection created a credibility problem that scientists did not choose. Even when the geology was straightforward, the communication environment was adversarial. In that environment, uncertainty was not treated as a normal feature of discovery. It was treated as a weakness that opponents could exploit, or as a gap that storytellers could occupy. The far side became a stage where two kinds of uncertainty overlapped. One was scientific uncertainty about lunar evolution, and the other was institutional opacity from Cold War practice. The first images therefore fueled suspicion in two directions. They revealed a startling difference, and they arrived through channels that were not designed for public trust. For believers in a cover-up, the gaps were the point. Low resolution could hide structures, partial coverage could omit anomalies, and processing could erase inconvenient details. The far side's unfamiliarity made it easy to project fantasies onto it, because no one had a mental baseline for what normal should look like. For scientists, the same gaps were an engineering reality. The moon was far, the signal was weak, and early spacecraft were fragile machines improvising in deep space. A camera had to survive radiation and temperature swings, a transmitter had to hold frequency stability, and ground stations had to pull meaning out of static. Both interpretations fed on the same fact. The far side had finally become data, but the data was incomplete and mediated. When evidence arrives through a chain of machines and institutions, the chain itself becomes part of the story, sometimes more than the evidence. As more strips of the far side were assembled, the language shifted from surprise to diagnosis. The far side was crater-saturated, Maria-poor, and apparently less resurfaced. In mosaics, the terrain looked like a dense field of overlapping bowls, with bright ejector rays and subdued rims hinting at different eras of impacts. That diagnosis raised a deeper question that the first images could not answer. What could cause a one-sided moon, with volcanism and composition distributed so unevenly? Was the difference written into the moon's formation? Or did it emerge later through a sequence of impacts and internal cooling that favoured one hemisphere? The early photographs did not show alien bases or impossible geometry. They showed a world that looked more ancient than expected, and therefore more informative than expected. The far side became a kind of control sample, less altered by lava, more faithful to the early bombardment record, and more demanding of careful interpretation. They also showed how quickly mystery can be manufactured from limitations. When a picture is grainy, every shadow can become a story, and every omission can become a motive. A scan line can look like a deliberate blur, and a missing strip can look like a censored zone, especially when the broader culture expects manipulation. The far side's difference was real, but its meaning was not settled. The first contact created a new kind of suspense, because evidence had arrived without closure. In science, that is normal, but in public imagination it feels like a cliffhanger, an unanswered question hanging in the static between worlds. From this point on, each mission would reduce one uncertainty while exposing another. Better images would clarify terrain, but they would also reveal new asymmetries to explain. Each improvement in resolution would remove one refuge for speculation, while simultaneously adding detail that demanded new models. And the more we mapped, the more the far side looked like a different world. That difference forces the next step, to ask what physics could make one hemisphere diverge. In the next chapter, we follow the competing explanations that emerged from these first maps. We test how heat, crust thickness, and impacts could build a lopsided moon. The first far-side photographs did more than surprise the public, because they overturned a comfortable assumption about planetary sameness. When Lunar 3 returned its ghostly smeared frames in 1959, the message was still unmistakable. This hemisphere was not simply the near side with different lighting. The far side looked brighter, rougher, and more crowded with craters, as if it had refused the dark, smooth floods that define the familiar face. Those early images forced a scientific question that still feels like a provocation, even after decades of mapping. If the Moon is one body born from one origin, why does it wear two geologic faces? The near side is Maria-rich and chemically distinct, while the far side is highland-dominated and stubbornly resistant to flooding. This chapter treats that split as the real mystery. A natural asymmetry can look like intentional concealment when you do not know the mechanism, and the Moon's tidally locked stare makes that suspicion almost too easy. We see one hemisphere every clear night, yet the other remains psychologically distant, present, mapped, and still somehow withheld. Start with what we can measure without touching the surface, because the Moon reveals itself through motion before it yields rock. Orbiters feel the Moon's gravity as tiny accelerations and decelerations, and those changes show up as subtle timing shifts in radio signals sent back to Earth. Track the spacecraft precisely, and you map mass beneath the crust, turning orbital dynamics into a kind of remote seismology. Gravity mapping works because mass is not evenly distributed, even inside a body that looks smooth from far away. Dense rock pulls harder and makes an orbiter speed up slightly, while less dense regions pull less, and the orbiter lags by a measurable amount. The effect is small, millimeters per second in velocity, but it accumulates over each pass until patterns emerge. In practice, the measurement is a choreography of clocks and antennas. A ground station transmits a stable radio tone, the spacecraft transpons it back, and analysts read the Doppler shift like a heartbeat. Where gravity strengthens, the frequency rises. Where it weakens, the frequency falls, and the map becomes a ledger of hidden weight. Add topography, and the puzzle sharpens, because height and mass do not always agree. Laser altimeters send pulses that bounce off the regolith and return in fractions of a second, building a global relief model with kilometre-scale precision. Stereo imaging adds texture and context, letting ridges, basin rings, and lava plains stand out as three-dimensional forms. Gravity gives subsurface mass, while topography gives surface shape, and together they reveal how much support comes from crustal thickness. A high region with low gravity implies light, thick crust, while a low region with high gravity hints at dense fill or uplifted mantle. It is an accounting problem. How much mass should be there, and what must be missing or added to make the numbers balance? On the near side, many large basins sit under positive gravity anomalies, and that association is too consistent to ignore. These are mascons, mass concentrations tied to basalt fill and uplifted mantle, and they are the Moon's most famous gravitational fingerprints. They show that impacts and later volcanism change density at depth, leaving behind a structure that still tugs on passing spacecraft. Visually, the near-side's basins read like ink stains on pale paper. Mare Imbrium, Serenitatis, and Chrysium look calm and flat from orbit, but gravity says they are heavy, as if the Moon buried something dense beneath a smooth lid. The basalt that flooded these basins is richer in iron and titanium than the anorthosite highlands, and that chemistry translates into a stronger gravitational pull. On the far side, the gravity field looks different in the aggregate, even though impacts are everywhere. There are fewer Maria-related mascons and more signals consistent with thicker, lighter crust, especially across broad highland provinces. The far side behaves more like an unmodified shell, where ancient crust remains the dominant architecture, and later flooding rarely broke through. The key inference is crustal thickness, because thickness is both structure and history. A thick crust is a stronger lid over the mantle, able to resist fracturing and to choke off rising melts before they reach the surface. A thin crust is a weaker lid that cracks and vents more easily, especially when impacts punch through and open deep pathways. Modern missions refine this with Grail-style logic, and the improvement is not subtle. Two spacecraft in formation measure distance changes as gravity varies, and even micrometer scale shifts matter when the baseline is long and the tracking is continuous. That yields a high-resolution gravity map that can be paired with topography to estimate crustal structure, basin compensation, and hidden intrusions. Grayle's achievement was to turn the Moon into a laboratory for gravitational field theory at planetary scale. Instead of one orbiter being tracked from Earth, the twin spacecraft tracked each other, reducing noise from Earth-based geometry and revealing finer details. In the resulting maps, basin rings appear not only as scars on the surface, but as deep patterns in density that persist through the crust. The broad result is persistent, even as models vary in their assumptions about density and porosity. The far-side crust is generally thicker than the near-side crust, and the hemispheric trend is hard to erase without breaking other constraints. Some estimates place the far side tens of kilometers thicker on average, which is enormous on a world whose crust is already thin compared to Earth's. Thickness alone explains part of the Maria mismatch, and it does so in plain physical terms. Basaltic magma needs buoyancy, fractures, and time, and it must remain molten long enough to rise without freezing in place. A thicker crust increases the pressure barrier and reduces eruption probability, while also providing more cold rock that can steal heat from ascending melt. But thickness is not the whole story, because heat drives melt, and melt is the currency of volcanism. The near side was hotter for longer in the regions that later erupted, and that longevity matters because the Moon's interior has been cooling for billions of years. The question becomes why heat and melt were so uneven, when the Moon is small enough that you might expect it to cool quickly and uniformly. Internal heat comes from two sources, and both are legacies of violent beginnings. One is leftover heat from formation and early impacts, stored in a body that was once far warmer than it is now. The other is radiogenic heat from radioactive elements decaying inside the Moon, a slow burn that can keep rock near its melting point long after the surface has frozen. Radiogenic heating depends on chemistry, which means it depends on where certain elements ended up during differentiation. Potassium, thorium, and uranium matter because they generate heat over billions of years, and their decay chains release energy steadily rather than in bursts. Where they concentrate, the mantle stays warmer and melts more readily, and where they are scarce, cooling wins sooner. This is where creep enters the story, not as a curiosity but as a diagnostic signature. Creep is shorthand for potassium, rare earth elements, and phosphorus, and it marks a geochemical residue left behind when the Moon differentiated. In simple terms, it is what remains after the first, most common minerals have crystallized out, leaving a melt enriched in the elements that do not fit easily into early crystals. The leading picture begins with a lunar magma ocean, a phase that is both dramatic and surprisingly constrained by evidence. Early on, much of the Moon was molten or partially molten, either from the energy of formation, from impacts, or from both. As it cooled, minerals crystallized and separated by density, and that separation created layers that still influence the Moon's behavior. Light plagioclase floated and built an anorthositic crust, which is why the highlands are bright and feldspar-rich. Denser minerals sank and formed mantle layers, including olivine and pyroxene that are darker and heavier. Incompatible elements that did not fit early crystals stayed in the last melts, and those melts became chemically distinctive reservoirs. Those late melts became enriched in creep-like components, and the enrichment is not just chemical decoration. They also carried heat-producing elements, which means they stored a long-term thermal advantage in specific regions. That enrichment is a heater embedded in the Moon's interior, subtle in concentration but powerful in consequence over geologic time. The near side hosts a major creep-rich province, and its footprint is visible in orbital element maps. It overlaps the Procellarum region and many Maria, creating a geographic coincidence that reads like causality. The far side shows far less of this enrichment on average, which implies a different thermal history even before you consider crustal thickness. Orbital gamma ray and neutron spectrometers help build that picture, because they detect element-related emissions from the top layer of regolith. When cosmic rays strike the surface, they trigger secondary particles and gamma rays that carry chemical information back to detectors overhead. The technique is indirect, and it averages over depth and mixing, but it is global, and global coverage is exactly what the far side needs. This chemical asymmetry makes the thermal asymmetry plausible, and it does so without invoking exotic causes. More heat-producing elements mean more internal heat, and more heat means more partial melting and more basalt available to erupt. If one hemisphere starts with a richer radiogenic budget, it can remain volcanically capable while the other becomes locked under a cooling lid. Now connect heat to crust thickness, because the two effects reinforce each other. A warmer mantle produces more melt, and that melt can pond at the base of the crust, pressurizing fractures and exploiting weaknesses. A thinner crust offers easier pathways, and when impacts add fractures, the system becomes primed for eruption. Put them together and the near side becomes the favoured outlet, not because it is chosen, but because it is permissive. The far side, with thicker crust and less radiogenic enrichment, becomes a place where melt may form less often and stall more easily. The result is not a single switch, but a long bias that accumulates into a visible dichotomy. Impacts then amplify the difference, and this is where the moon's battered face becomes part of the mechanism. Large basin-forming impacts thin crust locally and fracture it deeply, and the shock can also alter rock properties, increasing porosity and changing how heat moves. Those basins become low containers where lava can pool and spread, creating the smooth, dark plains that stand out even to the naked eye. The near side contains several enormous basins that later filled with basalt, and their outlines still shape the Maria's borders. The far side has large basins too, but fewer became dark Maria at the same scale, and the contrast remained striking in global mosaics. The lid and the heat budget likely differed, and that difference decided whether a basin became a lava sea or a cratered relic. Volcanism on the moon is not like Earth's plate-driven volcanism, and that distinction matters for how we interpret the surface. It is mostly a story of internal cooling, localized melting, and eruption through fractures, without the constant recycling that plate tectonics provides. Once the moon cooled, the window for widespread flooding closed, and the surface became a record rather than a work in progress. That timing matters for the dichotomy, because the mare basalts are not evenly distributed in age. If the near side stayed warm longer, it could erupt later, even after the far side had effectively shut down. If the far side cooled faster, or had less radiogenic heating, it would stop producing large melt volumes earlier, leaving impacts as the dominant resurfacing process. So the near side got resurfaced, and resurfacing is a powerful editor of planetary history. Basalt floods buried older craters and smoothed large areas, reducing relief and creating plains that look younger at a glance. The far side kept its older face exposed and accumulated impacts without being repaved, so its crater density climbed and its scars remained sharp. This is why the far side looks older without requiring older rock everywhere, and that nuance is easy to miss. It may be older surface exposure rather than older formation, which is a different claim with different implications. Resurfacing resets the crater clock, so a lava plain can be younger than the crust beneath it, while a highland surface can be ancient simply because nothing has covered it. The asymmetry also appears in heat flow hints, though the evidence is uneven by geography. Apollo heat flow probes sampled only the near side and they measured modest heat escaping, values consistent with a small body that has largely cooled. Models suggest the near side may still have higher heat flow than the far side, but direct far side measurements are scarce, and scarcity keeps the debate alive. That scarcity is important for the documentary's tension, because it is not merely a data gap. The far side is not only different, it is also undersampled, which makes every model feel provisional, even when the physics is sound. Now we turn to competing hypotheses, because no single mechanism is universally accepted. Each hypothesis tries to explain why chemistry, crust, and volcanism diverge by hemisphere, and each one must fit gravity, topography, and geochemistry at the same time. The difficulty is not a lack of ideas, but the fact that the moon's early history is partly erased by the very processes we are trying to reconstruct. One class of ideas starts at the beginning with the giant impact, because origin stories can preload asymmetry. If the moon formed from debris after a collision, the initial disk could have been compositionally uneven, with temperature gradients and mixing limits. Accretion could have locked in asymmetries before the moon fully cooled, leaving one hemisphere subtly different in the ingredients that matter for long-term heating. Some models propose that the impact delivered material unevenly, or that the moon accreted in a way that left one hemisphere richer in certain components. That would seed later differences in heat production and melting, and those differences would then cascade into crustal structure. The idea is not that the moon was built in two halves, but that early heterogeneity could survive longer than intuition suggests. Another class focuses on asymmetric crystallization of the magma ocean, which is plausible if cooling conditions varied across the surface. If cooling was not uniform, the flotation crust could thicken more on one side, and that thickness difference would influence everything that followed. A thicker anorthosite lid would insulate differently, fracture differently, and resist magma ascent more effectively. A related idea uses earthshine heating, and it is one of the most visually compelling explanations. Early Earth was hot and bright after the impact, radiating intense heat toward the near side, which would have been the hemisphere facing Earth for long stretches. The near side could have cooled more slowly, delaying crust formation there, while the far side radiated freely into space and solidified earlier. If the near side crust formed later or thinner, it would be easier to breach, especially once impacts began to punch holes in it. If the far side cooled faster, it could build a thicker anorthosite lid, and that lid would persist as a barrier long after the initial temperature gradient faded. The early thermal gradient would not need to remain forever, because the structure it produced could carry the memory. Earthshine also interacts with tidal locking, and the timing matters more than the concept. If the moon became synchronous early, one hemisphere faced Earth during critical cooling stages, and that fixed geometry could bias the thermal environment. Even partial locking, or a slow drift towards synchrony, could still create a persistent difference in how quickly crust crystallized and thickened. Another hypothesis invokes late accretion and impact history, shifting the emphasis from formation to bombardment. After crust formation, the moon continued to be hit, and the distribution of large impacts can reshape a hemisphere's prospects for volcanism. If large impacts were statistically clustered on one hemisphere, they could thin crust and trigger volcanism preferentially, even if the initial conditions were only slightly uneven. This is difficult to prove because impacts are stochastic, and randomness can imitate pattern when sample sizes are small. Yet a few enormous basins can dominate later evolution, and the moon has several that are large enough to matter globally. A single basin can create fractures, uplift mantle, and provide a low depression for lava, so the difference between one basin and none is not incremental. There is also a hybrid view that combines several effects, because nature rarely chooses only one lever. A small initial asymmetry in composition or crust could be amplified by impacts, and impacts could then focus volcanism where melt was already more available. In that framing, the dichotomy is not a single event, but a feedback loop between heat, structure, and chance. Creep distribution becomes a key constraint in these debates, because it is both a tracer and a test. If creep is a late-stage residue, why is it concentrated on the near side, and why does it align with major mare provinces? Did it migrate? Did it get exposed? Or was it emplaced unevenly from the start? Some models suggest creep was globally present, but later buried on the far side by thicker crust, leaving only faint orbital signatures. Others suggest it was never evenly distributed due to asymmetric magma ocean dynamics, perhaps shaped by early temperature gradients and convection patterns. The data can be read both ways depending on assumptions about mixing, burial depth, and how regolith gardening blurs chemical boundaries. Gravity and topography add another constraint, because structure must match mechanics. If the far side crust is thicker, the moon's centre of mass and figure should reflect that, and the observed gravity field must remain consistent with tidal and rotational evolution. The moon's long-term orientation may also be connected to internal mass distribution, because a body tends to present its heavier side toward its primary over time. This is where the mystery can masquerade as a cover-up. The far side is different in ways that require indirect inference, and indirect inference always leaves room for alternative stories, especially when the subject has a cultural history of secrecy. When the evidence comes as processed maps and statistical inversions, the gap between what is known and what is felt can widen. A skeptic can say the models are tuned because the far side is inconvenient to sample, and because the most famous samples came from the near side. A scientist can say the models are constrained because gravity and geology are consistent, and because independent instruments converge on similar trends. Both positions feed on the same gap in direct ground truth, and that gap is real even when the conclusions are solid. The documentary's central question returns here in a sharper form, and it is less about suspicion than about humility. What is actually on the far side, and why is it so different when the moon is small and should be simple? If nature can split a world so cleanly, we must ask what else our maps might be missing, and what biases we have built into our expectations, so we inventory what the data does and does not say, because clarity is the antidote to myth. It says the far side has thicker crust on average, and it says the near side is enriched in heat-producing elements and shows more volcanic flooding. It says impacts and volcanism interacted, and it says the timing of cooling mattered. It does not say the far side is artificial, and it does not say there are hidden structures waiting to be revealed by a single photograph. It does not even say we have sampled the far side enough to close every loophole, because sampling is still sparse and uneven. The moon is mapped at global scale, yet verified at local scale, and those scales do not always agree cleanly. The most productive tension is not between science and fantasy. It is between what we can infer globally and what we can verify locally, which is a normal tension in planetary science. The far side remains a place where inference leads and verification follows, and that ordering keeps the story open. That tension is amplified by how the moon is mapped, because maps are not raw reality. Gravity maps are processed products that require modelling choices about density, crustal porosity, and how topography is compensated at depth. Element maps from gamma-ray and neutron spectrometers require calibration, and assumptions about regolith mixing, depth sensitivity, and the smoothing needed to reduce noise. Even when the processing is honest, it is opaque to non-specialists, and the opacity can be mistaken for concealment. Opaqueness can look like secrecy when the subject already carries a myth of hiding, and when the far side's name itself suggests a forbidden half. The moon does not help us here, because its locked rotation makes the unseen hemisphere feel like a deliberate act. Still, the asymmetry is not a failure of understanding, and it is not a flaw in the data. It is a clue to early planetary evolution, preserved on a world without oceans, weather, or plate tectonics to erase it. It suggests the moon did not cool as a uniform sphere, and that early conditions mattered for billions of years, leaving a permanent signature in crust and chemistry. It also reframes the far side as a preserved half of a world, and preservation is a scientific gift. Fewer Maria means more ancient crust exposed, and that makes the far side a better archive of early impacts and crust formation. When you look at the far side's dense crater fields, you are looking at time made visible, a surface that has been counting collisions for eons. The far side is also a quiet platform in radio terms, and quiet is rare in modern space. Shielded from Earth's transmissions, it could host low-frequency radio astronomy that is nearly impossible from the ground, listening for signals from the early universe and distant plasma environments. That scientific value can coexist with mystery without requiring hidden motives, and it can turn the far side into a destination for reasons that are practical rather than theatrical. But the narrative hook remains because the far side is where our certainty thins and where the moon's two faces feel most symbolic. We can map it, yet we cannot casually visit it, and we still rely on a small number of missions for much of what we claim to know. We can infer crust and chemistry, yet we still lack widespread samples that would settle arguments about origin and evolution. This chapter's conclusion is a pivot, because the moon's two-faced geology is strange enough to feel staged even when it is natural. The more we learn, the more the mystery becomes about origins rather than concealment, and about early physics rather than late secrets. The far side stops being a blank and becomes a test of how well we can read a world from afar. Next, we follow the data deeper into the far side itself. We move from hemispheric averages to specific anomalies that people cite as evidence of something withheld. We ask which anomalies survive better instruments and which dissolve under resolution. On the far side, the moon stops looking like a face and starts looking like evidence, as if the familiar portrait has been turned over. The near side's dark Maria distract us with patterns that feel readable, even friendly, because they carry names and myths. The far side's crowded scars insist on a harder story about early time, less like scenery, more like a forensic record. If the documentary's central question asks what is on the far side, this chapter answers with impacts, written at basin scale. Not just ordinary craters, but continent-sized wounds that rewrote crust, gravity, and memory in a single event. The far side is where the moon kept more of its earliest pages, because fewer later floods came to blur the ink. Start with the landmark that dominates every serious map of the far side, even when labels are stripped away. The South Pole, Aitken Basin, spans roughly 2,500 kilometers across, curving from the lunar South Pole toward the far side equatorial highlands. In planetary terms, it is a structural province, not a feature, one of the largest known impact structures in the solar system. Its size implies a collision beyond everyday intuition, because only rare bodies carry enough momentum to carve that much rock. The impactor was likely tens to over 100 kilometers wide, arriving at several kilometers per second on a steep, unforgiving trajectory. The energy release rivals global catastrophes on Earth, but here it is delivered in minutes, not millennia. an instant that left a signature lasting billions of years. A basin that large is not a simple hole, and it is not even a single rim you can trace cleanly. It is a multi-ring structure with a deep interior, uplifted rims, and faulted terraces that mark where the crust failed under stress. It reshapes regional crust thickness and leaves a long-lived gravitational and compositional signature, which orbiters can detect without ever touching the surface. Even the way it appears on screen tells a story if we linger on the lighting. Low sun angles turn the basin's subtle rings into faint circular shadows, as if the moon is showing us the outlines of an ancient bruise. At higher sun, those same rings almost disappear, and the basin becomes a broad, muted depression, evidence that the biggest events can leave the quietest topography. The basic physics is accessible if we keep the sequence clear and resist turning it into magic. First comes contact and compression, when shock waves race through rock faster than sound and briefly push minerals into exotic high-pressure forms. Pressures rise so high that crystal lattices collapse and temperatures spike, even though the moon has no air to burn. Then comes excavation, when material is thrown outward and upward in a transient cavity that is deeper than the final basin. The excavation flow is not a simple splash, because rock behaves like a fluid under extreme shock, then snaps back toward brittleness as pressure drops. In that short window, the moon's crust is both solid and not solid, and the basin is being sculpted by physics rather than erosion. Excavation depth matters because it tells us what layers were exposed, and therefore what chemistry might be sampled at the surface. Small craters mostly churn regolith and shallow crust, mixing dust and broken rock like a slow blender. A megabasin can punch through much of the crust and disturb the upper mantle, which is why South Pole, Aitken, is treated like a natural probe. After excavation comes modification, when gravity collapses steep walls and the transient cavity relaxes toward a stable shape. Central peaks rise as the floor rebounds from shock unloading, bringing deeper material upward like a slow-motion splash frozen in stone. In the biggest basins, rings form as the crust fails in broad circular faults, and the surface records that failure as concentric arcs. Heat is part of the scar, not a side effect that can be ignored once the crater is drawn. The shock melts rock into vast melt sheets that can pool across the basin floor and along terraces, then cool into coherent layers. Those melt sheets reset local geology and can preserve chemical clues from depth, because they incorporate fragments from multiple levels of the crust. In close-up visuals, impact melt can look deceptively smooth, like cooled lava, but its origin is different. It is made in an instant, not fed by a long-lived magma system, and it often traps breccias, angular blocks suspended in frozen melt. That texture matters, because it tells us the basin is a mixing machine as well as a whole. Ejecta blankets spread the violence across continents of lunar terrain, and they do it with a geometry that can be mapped. Material launched ballistically falls back in curtains and rays, landing at speeds that still fracture and melt. Thick ejecta can bury older craters until only ghost rims remain, while thin ejecta can only soften their rims and mute their relief. This is why basins are time machines as well as wounds, and why their deposits are treated like stratigraphic markers. They excavate deep material and then lay down a datable layer, at least in relative terms, across huge distances. They create a before and after boundary that crater counts can read, provided the surface has not been resurfaced later. South Pole, Aitken, is especially valuable because it sits on the far side's older crust, where the background is already ancient. The far side lacks widespread mare flooding that would later erase basin textures and bury ejecta under basalt. The basin's interior and rings remain more legible than many near-side counterparts, which were later overprinted by dark volcanic plains. Yet the far side is not only South Pole, Aitken, and the camera should not let it become a single feature story. It is a hemisphere of overlapping basins, crater chains, and saturated highlands, where circles cut circles and arcs fade into arcs. The density is so high that older craters are often only inferred from ghost rims, subtle topographic lows and partial ring segments. Crater saturation is not just a visual impression, and it is not merely a poetic way to say busy. It is a statistical regime where new impacts destroy evidence of earlier ones, pushing the surface toward an equilibrium of damage. Even so, the far side still preserves relative sequences better than the near side's resurfaced plains, because fewer later lavas arrive to reset the count. To turn scars into chronology, scientists use crater counting, which is both simple in concept and demanding in practice. On an airless body, impacts accumulate and persist for billions of years because there is no rain to wash them away. A surface with more craters is usually older than a surface with fewer, but the sizes and degradation states matter as much as the raw number. Crater counts are built from catalogues, and catalogues are built from images, lighting choices, and human judgment. Small craters can be missed in harsh shadows, while degraded rims can be misread as ridges or wrinkles. That is why modern counts often combine multiple illumination angles and use automated detection as a check, yet the final chronology still carries uncertainty. The method is comparative, not absolute, unless it is anchored to samples returned to Earth. Apollo and Lunar samples calibrate parts of the near-side's timeline, tying crater densities to radiometric ages measured in laboratories. Far-side ages rely more heavily on model curves and cross-basin comparisons, because we do not yet have the same ground truth from those older terrains. Even with that limitation, the far side offers a clearer window into early bombardment, because fewer young basalt plains reset crater clocks. It has more ancient highlands that preserve the early impact flux, even when that flux becomes hard to separate from saturation. In other words, the far side is messy, but it is an old mess, and that is exactly what we need. This matters because the early solar system was not gentle, and the Moon formed into a neighbourhood still full of debris. After planet formation, leftover planetesimals and fragments still crossed unstable orbits, nudged by resonances and close encounters. The Moon, lacking atmosphere and oceans, recorded that chaos directly, and it did so with a fidelity Earth could not maintain. The Moon is often described as a witness plate, and the metaphor holds because the Moon does not recycle its face. Earth's early surface was reworked by plate tectonics, weather, and erosion, and even the oldest surviving terrains have been altered repeatedly. The Moon kept the scars that Earth likely lost, which makes lunar basins a proxy for Earth's missing history. So when we study far-side mega-craters, we're not only studying the Moon, we are reconstructing the environment that shaped Earth's habitability, because impact rates and impact sizes influence oceans, atmospheres, and the survival of early life. The same populations that struck the Moon were also crossing Earth's orbit, and Earth's larger gravity would have drawn in even more. Here the story connects to a long argument in planetary science, one that has shifted as new data arrived. Was there a discrete spike in impacts around 3.9 billion years ago? A sharp cataclysm that punctuated early history? Or was there a smoother decline from an initially high bombardment rate, where the apparent spike is partly an artifact of where we sampled? This is the late heavy bombardment debate, and the far side is central to it because it may preserve basins older than the ones we know best. Near-side sample ages cluster in ways that can reflect real spikes or sampling bias, because Apollo landed where it could, and where the terrain was accessible. Far-side terrains may preserve older basins that test whether the spike was global, regional, or even illusory. If South Pole, Aitken, is older than the classic near-side basins, it pushes the timeline back and expands the early chapter we're trying to read. If its crater statistics fit a steady decline, it weakens the need for a sharp cataclysm and favours gradual clearing. If it shows evidence of a later surge, it supports a reorganised solar system, where dynamics changed suddenly rather than slowly. The debate is not academic, because it ties directly to planet migration models that attempt to explain the modern layout of the solar system. In the Nice model family, giant planets shift orbits and destabilise small body reservoirs, scattering objects inward. That instability can send comets and asteroids toward the inner planets in waves, leaving signatures that a cratered surface might preserve. Lunar basins constrain those models by acting as timestamps, even when the timestamps have error bars. Each basin is a data point on impactor size distribution and frequency, and each ring system is a record of energy and target properties. A hemisphere that preserves older terrain increases the number of usable data points, which is crucial when the early record is sparse. Impact physics also constrains the nature of the impactors, because different populations arrive with different speeds and angles. Basin morphology, melt volume, and ejector distribution depend on velocity, density, and impact geometry, and those variables are not random. Different source regions produce different typical velocities at the Moon, and those differences can subtly shape crater populations. Asteroids from the inner belt tend to have different encounter speeds than comets from farther out, and they may carry different volatile inventories. If crater populations shift in subtle ways, they hint at changing source reservoirs over time, even if we cannot name each reservoir with certainty. The far side's older surfaces are where those shifts are most likely recorded, because fewer later events have overwritten them. South Pole, Aitken also raises a compositional question that points forward, and it is one of the basin's most compelling scientific hooks. If the basin excavated deep crust or mantle, its floor should differ chemically from surrounding highlands, which are dominated by anorthositic crust. Orbital spectroscopy and gamma-ray data look for that difference, scanning for mineral fingerprints and elemental abundances. Some measurements suggest enhanced mafic signatures in parts of the basin, which would mean more iron and magnesium-rich material than typical highlands. That would be consistent with deeper material exposed, or with later volcanic infill that exploited the basin's thinned crust. Either way, the basin becomes a natural drill hole into the moon, created by violence but useful for science. The word mafic can sound abstract, so we translate it into imagery the viewer can hold. Mafic minerals like olivine and pyroxene absorb and reflect light differently, changing spectral slopes in ways instruments can detect from orbit. On maps, those differences become patches of colour-coded data, quiet, technical overlays that reveal a hidden mineral landscape beneath the dust. But the far side's archive is complicated by later overprinting, even when it avoids the near side's great basalt floods. Even ancient highlands are not untouched, because smaller impacts churn regolith continuously in a process called gardening. This gardening mixes ejecta, blurs boundaries, and slowly erases fine stratigraphy, turning crisp layers into a stirred, dusty palimpsest. Regolith itself is part of the story because it is not just soil, but a record of micro-impacts and solar wind implantation. Each grain has been shocked, melted, and welded into agglutinates, and each surface has been exposed to radiation. On the far side, where surfaces can remain exposed for immense spans, regolith can become a deep, complex archive of bombardment and space weathering. Still, the far side preserves more than it loses, compared with the near side, and the contrast is visible even at global scale. Nearside maria bury enormous areas under basalt that can be kilometers thick, smoothing relief and erasing older crater populations. That burial hides older basins and removes early crater fields from view, which is why the near side can look younger than it really is. This is why the far side's violence is scientifically useful, and why more battered is not the same as less informative. It is not simply more cratered, it is less edited, with fewer resurfacing episodes that reset the clock. It retains older crater fields that approximate the early bombardment surface, even when saturation makes the counting difficult. The chapter's mysterious tone belongs here, because the far side looks like a crime scene lit by grazing sunlight. The evidence is everywhere, but the event is long past, and the perpetrator is not a single object. We reconstruct the culprit by reading patterns in broken rock, rings, rays, melt deposits, and the statistical language of crater populations. Make the scale personal without exaggeration, and let the visuals do some of the work. A basin-forming impact would have lit the lunar surface with incandescent ejecta, arcing above the horizon in glowing sheets. It would have shaken the moon globally, sending seismic waves through a body still warm inside. And those waves would have reverberated through fractures for hours. Those waves matter because they can fracture crust far from the basin, creating networks of weakness that persist. Fractures become pathways for later melts, if melts exist and if pressure conditions allow ascent. On the near side, that pathway story helped create Maria, because heat and magma were available. On the far side, the pathways often led nowhere, leaving fractures without floods. So the far side's mega craters also reinforce the earlier asymmetry story, but they do it with mechanics rather than mystery. Thick crust and lower heat budgets limited later flooding, even when impacts created the structural space for it. The far side kept its basins as basins, rather than turning them into dark plains, and that preservation makes the far side feel older at a glance. This is where suspicion can attach itself to real geology, because a hemisphere that preserves older scars can look like a deliberately hidden record. But the simplest explanation is that resurfacing differed, not that images were suppressed or histories erased by design. The far side is remote in the literal sense, and remoteness always invites stories, yet the rocks tell a straightforward one. The cover-up framing still has a role, because it mirrors how data arrives in the modern era. We see processed maps, crater catalogues, and model ages, not raw history. and those products carry choices about filters and thresholds. The far side's remoteness makes every inference feel like a decision, which is why transparency about uncertainty becomes part of the narration. So we emphasize what is measurable and what is uncertain, and we keep those categories distinct. Basin sizes and crater densities are observable from orbit, and topography can be measured with laser altimetry and stereo imaging. Absolute ages depend on calibration and assumptions about impact flux over time, which is why models can disagree even when the images look the same. We also emphasize why the far side is the best place to reduce that uncertainty, and why the next steps are so often about samples. Sample return from far side basins would anchor crater chronology earlier than Apollo, extending the radiometric timeline into older terrain. It would test whether the early impact flux had spikes, lulls, or a smooth decay, and it would narrow the range of plausible solar system histories. The far side's crater fields also help estimate the size distribution of early impactors, which is a quiet but powerful constraint. Big basins require rare large bodies, while small craters reflect abundant small debris, and both populations evolve with time. The ratio between them constrains how debris populations changed, and it hints at whether the source was mainly asteroidal, cometary, or mixed. That ratio matters for Earth's early environment because impacts are both destructive and constructive depending on size and timing. Too many large impacts sterilize surfaces and strip atmospheres, while too few impacts reduce delivery of volatiles and organics, depending on source. Habitability sits between extremes, and the Moon helps bracket them by preserving a more complete impact ledger. Now return to South Pole, Aitken as the chapter's anchor beat, and let it hold the frame as we gather implications. Its rim-to-rim span suggests a collision that excavated enormous volumes, throwing material across the far side and beyond. Its depth and gravity signature imply crustal thinning and possible mantle uplift, which is why it remains a priority target for orbital mapping and future sampling. Gravity data, in particular, turns absence into information, because it reveals mass anomalies beneath the surface. A thinner crust or denser mantle material closer to the surface changes the local gravitational field, and orbiters feel that change as tiny accelerations. Those accelerations become maps, and those maps become hypotheses about what lies beneath the dust. If mantle material is present near the surface, it changes the mineral story in a way that is both specific and testable. Olivine and pyroxene signatures would indicate deeper origins than an orthosite, and they would reshape models of lunar differentiation. That possibility sets up the next chapter's focus on minerals and chemistry, because composition is the language that impacts expose. The chapter also needs a clear statement about why far-side terrain is older, and it should be said without overclaiming. It is older in exposure age because it avoided widespread mare resurfacing that would have reset crater counts across vast areas. It may also include older crustal units that predate many nearside plains, which makes it a better place to look for the earliest basin record. We close by widening from lunar geology to solar system dynamics, because the far side is not an isolated oddity. The Moon's far side is a preserved record of the same instability that shaped Earth and rearranged planets, and it carries that record in plain sight. When we read it carefully, we are reading a chapter of our own planet's prehistory, written in rings and fractures. If the far side is an archive, then the next question is what the archive is made of. Minerals, chemistry, and subtle traces of water decide how we interpret the scars, and they decide which hypotheses survive contact with data. In the next chapter, we move from impacts to ingredients, trading crater rims for spectral lines and elemental maps. We keep the central question alive as we transition, because the far side refuses to be reduced to a single reveal. What is on the far side is not one secret object, and it is not one tidy explanation. It is a layered record of collisions, composition and time, waiting for better samples, sharper instruments, and a clearer way of listening. The far side looks unfamiliar because its surface is built from different ingredients, exposed in different proportions, and lit in ways that exaggerate contrast. That difference is real, yet it is also easy to misread when the evidence arrives as coloured maps, calibrated plots, and processed images. In the raw grayscale of an orbiter camera, the far side can look almost bleached, an ancient face with fewer dark stains, but brightness is not a simple aesthetic, and it is never a single measurement. It is a physical response to mineral chemistry, grain size, and the slow grinding of impacts. To ask what the far side is made of, we start with a rule of planetary science that is both empowering and limiting. Most of what we know comes from remote sensing, which means measuring light and particles instead of holding rocks. The moon is close enough to photograph in exquisite detail, yet far enough that most of its chemistry must be inferred. That inference is not guesswork, but it is also not direct touch. It is a chain of measurements, corrections, and models, each link strong, yet each link capable of bending. Remote sensing is not a single instrument or a single truth. It is a toolkit with strengths, blind spots, and failure modes that can mimic mystery. Different sensors sample different depths, different scales, and different physical processes. Some respond to the top few microns of dust, while others average tens of centimeters. Some are sensitive to minerals, others to elements, and others to texture. When those layers disagree, the mismatch can look like a secret, when it's often just physics. Reflectance spectroscopy is the most intuitive tool because it begins with sunlight, the simplest lamp in the solar system. Sunlight hits the regolith, some wavelengths are absorbed, and the rest are reflected back to an orbiter. The reflected light is not just brightness, but a spectrum, a curve that rises and dips with wavelength. Those dips are not decorative. They are the signature of electrons vibrating in crystal lattices, absorbing energy at specific bands. Minerals leave fingerprints because their crystal structures absorb specific wavelengths in predictable ways. Pyroxene and olivine show broad absorption bands near 1 and 2 microns, shaped by iron in their crystal sites. Plagioclase is brighter and more subtle, often lacking deep bands unless it contains trace iron or is mixed with darker phases. In practice, the spectrometer is listening for shallow whispers under loud noise. A few % of dark material can dominate the signal, especially when space weathering has already dimmed the scene. Spectrometers do not see bedrock directly in most places, and that matters for every dramatic claim. They see the uppermost skin of the moon, a mixed layer of dust and fragments constantly churned by impacts. This regolith is not a static blanket. It is a gardened zone, overturned by countless micro-impacts and punctuated by larger craters that throw debris for kilometers. Over time, the surface becomes a blended average of nearby materials. A spectrum can therefore be local, regional, and historical all at once. Space weathering complicates every spectrum we collect, and it does so in a way that can imitate a new mineral. Micrometeorites melt tiny patches of soil into glass, while the solar wind implants hydrogen and sputters atoms free. These processes create nanophase ion particles that darken and redden surfaces, masking fresh mineral signatures. The effect is strongest where the surface has been exposed longest. A mature soil can look compositionally different from a fresh one, even if the rock source is the same. So an unusual spectrum can mean unusual composition, or it can mean unusual maturity. It can also mean a fresh crater excavated deeper material, briefly revealing a truer signal before it weathers again. This is why planetary scientists compare crater rays, ejecta blankets, and interior walls. Fresh exposures act like accidental drill cores, short-lived windows into layers that are otherwise hidden. The far side, with its dense crater record, offers many such windows. It also offers many opportunities to mistake a temporary exposure for a permanent anomaly. Gamma-ray spectroscopy adds a different kind of evidence, and it does not rely on reflected sunlight. Cosmic rays strike the surface and excite atoms, which emit gamma rays at element-specific energies. The detector counts photons at those energies, building a spectrum of its own. Where reflectance spectroscopy is shaped by minerals, gamma rays are shaped by elements. It is a different language describing the same ground. Those energies tell us about thorium, potassium, iron, titanium, and other elements, averaged over broad footprints. The method is powerful for global maps, but it is coarse in resolution. A single pixel can cover a region large enough to swallow a city and its suburbs. That scale is perfect for hemispheric trends, and frustrating for small targets. It is also sensitive to statistics, because gamma rays are rare. The map is built from long accumulation times and careful background subtraction. Neutron spectroscopy pairs with gamma rays because cosmic rays also knock neutrons out of the regolith. Those neutrons scatter, lose energy, and leak back into space, where an orbiter can count them. Hydrogen slows neutrons efficiently, so a deficit of fast neutrons can indicate hydrogen enrichment. The physics is simple to state and tricky to interpret. Hydrogen can be water, hydroxyl, implanted protons, or even hydrogen-bearing minerals delivered by impacts. On the Moon, hydrogen often points to water-bearing compounds or implanted solar wind hydrogen. It also points to cold traps near the poles, where volatiles can persist for geologic time. Even away from the poles, subtle hydrogen signals can track soil maturity and solar wind exposure. That means a hydrogen map can be both a volatile story and a surface process story. The far side's hydrogen patterns are therefore not just a treasure hunt, they are a record of how the surface interacts with space. Radar adds yet another dimension, and it is often misunderstood in popular claims. Radar measures surface roughness and dielectric properties, and in some cases it hints at buried layers. A rough surface scatters the signal differently than a smooth one, and a dense material reflects differently than a porous one. At certain wavelengths, radar can penetrate a bit beneath the surface, but that penetration is limited, and it depends on frequency, composition, and the size of rocks within the soil. But radar does not produce X-ray vision of hidden bases, no matter how seductive the idea sounds. Its penetration depends on frequency and material properties, and its interpretations are ambiguous without context. A bright radar return can mean blocky ejecta, a young crater, or a rough lava flow. It can also mean a change in dielectric constant caused by composition. Without topography and optical imagery, radar alone is a Rorschach test. Each tool answers a different question, and each tool can be overextended. When people claim a single map proves an artifact, they usually ignore what the instrument cannot resolve. They also ignore that instruments do not measure objects. They measure signals that must be inverted into physical meaning. That inversion is where uncertainty lives. It is also where careful science earns its authority. Now, we apply the toolkit to the far side's most obvious trait. The far side is bright and highland-dominated, which is a compositional clue as much as a visual one. In wide-angle views, the hemisphere looks like a field of pale stone, scarred by overlapping craters. The maria that define the near side are mostly absent, so the eye is drawn to highlands that seem older, higher, and more heavily battered. Brightness here is not paint. It is mineralogy, and it is history. The bright highlands are rich in anorthosite, a rock dominated by plagioclase feldspar. Plagioclase is light-coloured and relatively low in iron, which raises reflectance. On the Moon, the most common plagioclase is anorthite, a calcium-rich end member that forms in specific conditions. When sunlight hits a feldspathic surface, it tends to scatter more efficiently. That scattering makes the landscape look chalky, especially at low sun angles when shadows carve every crater rim. This points back to the magma ocean model introduced earlier, now tested by mineral evidence. Early in lunar history, a global or near-global melt differentiated as it cooled. The idea has roots in Apollo-era debates, when returned samples showed ancient crustal rocks dominated by plagioclase. If the Moon once had a deep melt, then crystallization would have sorted minerals by density. The model is not a mythic origin story. It is a thermodynamic expectation for a hot young body. Dense minerals like olivine and pyroxene tended to sink, while plagioclase floated. That flotation built a primary crust, and the highlands preserve it. The physics is buoyancy, but the consequence is architecture. A low-density crust forms early, insulating the interior and controlling later volcanism. The thickness and continuity of that crust matter. They decide where magma can rise, where impacts can punch through, and where heat can escape. The far side's extensive anorthosite suggests that this flotation crust is more intact there. Fewer mare floods means fewer later basalts covering or mixing with the original crust. In images, the difference is stark. The near side's dark plains fill basins like ink, while the far side's basins often remain pale, their floors still dominated by highland material. That does not mean the far side never saw volcanism. It means volcanism was less efficient at resurfacing large areas. This is not just a story about colour. It is a story about density, buoyancy, and how a young moon sorted itself into layers. It is also a story about time, because the crust you see is the crust that survived. Every impact excavated, mixed, and redistributed material. Every eruption buried and reset surfaces. The far side's brightness is therefore an archive. It is a hint that the earliest crustal products remain closer to the top. The near side's maria are darker because basalt is richer in iron and titanium. Those elements lower reflectance and change spectral shapes, making mare plains stand out. Basalt also cools into fine-grained textures that weather differently than coarse highland rocks. In spectral terms, mare basalts tend to show stronger mafic absorption features. In elemental terms, they often carry higher FeO and TiO2. The near side is not just darker, it is chemically distinct in ways that align with volcanic resurfacing. So a simple observation becomes a compositional hypothesis. The far side should show less basaltic material at the surface and more feldspathic crust exposed. This is a testable claim, and it has been tested repeatedly as instruments improved. Early telescopic observers suspected differences, but they could not measure composition. Orbital missions changed that, first with broad brush maps and later with higher spectral resolution. The far side stopped being a blank, it became a dataset. Orbital spectroscopy largely confirms that expectation, but with important caveats. Some far side regions show stronger mafic signatures than the average highlands, especially around large basins. Basins are not just holes, they're excavators that dig deep and spread their spoil across enormous distances. Their ejector blankets can mix lower crustal material with surface anorthosite. They can also create impact melt sheets that cool into compositions unlike the surrounding terrain. South Pole, Aitken is central again because impacts excavate depth. If the basin exposed lower crust or mantle materials, it could create localized patches of pyroxene-rich or olivine-bearing signatures. The basin scale is difficult to hold in the mind. It is thousands of kilometers across, a scar that dominates the far side south. Along its rim and floor, subtle color differences in enhanced images correspond to real mineral variations. Those variations are clues to what lies beneath the crust. Those patches are scientifically valuable, but they are also a magnet for misinterpretation. A mineral anomaly can be framed as a deliberate deposit, when it is often excavation and mixing. The moon does not need intention to create a boundary. It needs energy, and impacts provide it in abundance. When a crater forms, it is not a neat sample. It is a chaotic blend of shattered rock, melted droplets, and redistributed dust. The anomaly is often a fingerprint of violence, not design. Now we move from minerals to elements because elemental maps sharpen the near side, far side split. The most famous element in this story is thorium, a tracer of incompatible, late-stage melts. Incompatible elements do not fit easily into early forming minerals, so they concentrate in the remaining melt as crystallization proceeds. That makes thorium a kind of dye in the lunar interior. Where it is high, something once concentrated the leftovers. Thorium is not important because it is dangerous or exotic. It is important because it tags the creep reservoir and correlates with heat-producing elements. Creep, potassium, rare earth elements, and phosphorus became a shorthand for late-stage lunar chemistry. In Apollo samples, creep-rich rocks suggested a final melt fraction, enriched in elements that refuse to crystallize early. Thorium travels with that enrichment, and it is easier to map from orbit. It becomes a proxy for a deeper story about differentiation. Global gamma-ray maps show thorium concentrated on the near side, especially around the Procellarum region. The far side shows much lower thorium on average, with smaller localized highs. On a color map, the near side glows with warm tones, while the far side cools to blues and greens. The pattern is not subtle. It is one of the strongest hemispheric chemical contrasts on any terrestrial body we have mapped this well. The question is not whether it exists. The question is what it implies. That pattern supports the earlier thermal argument without requiring a hidden mechanism. Less thorium implies less radiogenic heating, which implies less melt generation over time. Radiogenic heat is slow heat, the kind that matters after the early violence fades. If the near side retained more heat-producing elements near the crust, it would stay warmer longer. Warmer crust is more likely to crack, melt, and feed basaltic eruptions. The far side, with less of that budget, would cool more thoroughly and resist widespread flooding. Iron and titanium maps tell a related story, but they track different materials. High iron and titanium often mark mare basalts, and those are overwhelmingly near-side features. Titanium is especially useful because high-T basalts stand out clearly in remote sensing. When you see a titanium-rich patch, you are often seeing a specific volcanic lineage. The far side's low titanium is not a mystery substance. It is the expected signature of feldspathic highlands and limited basalt flooding. Rare earth elements are harder to map directly, but they travel with creep-like chemistry. Where thorium is high, rare earth enrichment is usually inferred, and that links chemistry to internal evolution. This is one reason thorium maps became iconic. They connect surface pixels to deep processes. They also connect modern orbital data to Apollo-era laboratory measurements. The Moon becomes a bridge between field geology and remote sensing, with each validating the other. These distributions are not random paint splatters. They reflect how the Moon differentiated, how melts migrated, and where impacts opened pathways through the crust. They also reflect the Moon's asymmetry in crustal thickness, which influences how easily magma can reach the surface. A thicker crust is a stronger lid. A thinner crust is a leaky one. The near side appears to have been the leaky side, and the chemistry agrees. They also reflect what we have and have not sampled. Most returned samples are near side, so far side element maps carry more uncertainty in calibration and ground truth. Apollo and Lunar missions landed where communication was easy, and where smooth mare plains offered safer terrain. That historical constraint shaped our rock collection. It also shaped public perception, because the far side remained a place of inference rather than souvenirs. The first far side samples returned by later missions are precious, partly because they begin to close that gap. That uncertainty is a real gap, and it feeds the cover-up narrative when people want it to. If you distrust the processing, every smoothing choice can look like deliberate hiding. A colour scale can feel like propaganda if you do not know why it was chosen. A missing data stripe can feel like censorship if you do not know the orbit geometry. Suspicion thrives in the spaces between raw counts and final maps. So we explain what processing actually does, because the steps are less dramatic than the rumours. Instruments collect noisy data along orbital tracks, then analysts correct for geometry, background radiation, and detector drift. They account for cosmic ray flux changes, detector temperature, and spacecraft altitude. They remove contributions from the spacecraft itself, because even the orbiter emits and scatters radiation. None of this is optional. Without it, the map would be a portrait of the instrument, not the Moon. Maps are gridded and smoothed because raw counts are sparse. Smoothing reduces noise, but it can also blur sharp boundaries and create false gradients. That trade-off is not a conspiracy. It is a statistical choice, and it is usually documented in mission papers. Scientists often provide uncertainty estimates, but those are easy to ignore in viral screenshots. The cleanest-looking map is not always the most honest. Sometimes the honest map looks messy. Resolution limits matter because a map pixel can represent tens of kilometers. A small feature can be diluted into its surroundings, or a mixed region can look like a single coherent unit. This is especially important for claims about structures. A structure is, by definition, localized, but many chemical maps are not built to resolve localized targets. They are built to reveal provinces, trends, and broad compositional terrains. When a low-resolution map is treated like a close-up photograph, misunderstanding is almost guaranteed. This is where the word unusual needs discipline. In planetary science, unusual often means statistically distinct from the local background. Not impossible, not artificial, and not unique. It is a flag for attention, not a verdict. A thorium hotspot can be unusual because it is higher than neighbouring pixels. It can still be a natural concentration produced by impact melt, volcanic residues, or excavated layers. The Moon has had billions of years to concentrate, disperse, and remix materials. A spectral signature can be unusual because it does not match common end members. It can still be explained by mixtures, grain size effects, or space weathering differences. Grain size alone can change band depth and brightness, because fine powders scatter light differently than coarse fragments. A fresh, blocky crater wall can look compositionally distinct from its own ejecta blanket. The difference can be physical texture rather than chemical identity. Remote sensing sees both at once, and it takes care to separate them. When claims of engineered structures appear, they often begin with a real anomaly. The leap happens when the anomaly is treated as a designed object instead of a geologic process. That leap is emotionally satisfying because it turns ambiguity into narrative. It also feels plausible because the Moon's surface is sharp-edged and high contrast. The Moon looks like it was carved. But carving is what impacts do. They carve without intention, and they leave geometry behind. False positives are common because the Moon is a harsh test for human perception. With no atmosphere, shadows are sharp, contrast is extreme, and the same terrain changes character with sun angle. A boulder can cast a shadow longer than a house. A shallow ridge can look like a wall when the sun skims the horizon. The far side, with its rugged highlands and dense crater fields, provides endless opportunities for this illusion. Low sun angles exaggerate relief and create long shadows that can resemble walls and towers. High sun angles flatten topography and can hide ridges that were obvious hours earlier. When a viral image shows a monolith, it is often a single lighting moment. Change the incidence angle, and the monolith becomes a mound. Change the viewing angle, and the straight edge becomes a curved rim. The moon is not changing. Our interpretation is. Compression artifacts add another layer of confusion, especially in older datasets. Blocky edges, ringing and banding can create straight lines and repeated patterns that look intentional. Early digital imagery often used aggressive compression to fit limited bandwidth. Even modern products may be downsampled for quick browsing, then reposted and recompressed again. Each generation of compression can sharpen false edges. A natural slope can acquire a digital staircase. Mosaics can also introduce seams that mimic linear features. When images taken under different lighting are stitched together, boundaries can look like constructed edges. A seam can run straight across a crater, ignoring topography, because it is not a feature on the ground. It is a feature in the dataset. The fix is simple but rarely done in online debates. You check the original frame boundaries, and you check independent mosaics made by different teams. Resolution limits create their own illusions. A feature smaller than a pixel becomes a smeared shape, and the brain fills in missing detail with familiar geometry. A few bright pixels can become a dome, a few dark pixels can become a doorway. The far side's psychological distance amplifies this effect. Because the unseen invites storytelling, the mind prefers an intentional pattern over an uncertain blur. This is pareidolia, and it is not a character flaw. It is a normal pattern recognition system operating on incomplete information. Evolution trained us to see faces in shadows and threats in the grass. On the moon, that same system sees architecture in crater rims. The scientific response is not to mock the impulse, but to test it. Curiosity is useful, it just needs a method. The far side is especially vulnerable to pareidolia because it is psychologically distant. People expect the unseen hemisphere to hold surprises, so ambiguous shapes are interpreted as messages. The phrase dark side still echoes in popular culture, even though the far side is not perpetually dark. That cultural residue matters. It primes the audience to expect secrecy. It primes them to treat ordinary uncertainty as evidence of concealment. The scientific response is not to mock the impulse, but to test it with cross-checks that are hard to fake. If a structure is real, it should persist across lighting conditions, viewing angles, and independent instruments. A true topographic wall should appear in laser altimetry and stereo-derived elevation models. A true compositional boundary should appear in multiple spectral datasets, not just one processed image. A true anomaly should survive reprocessing by different groups. When those cross-checks are applied, many viral anomalies dissolve. The feature shifts with illumination, disappears in higher resolution, or aligns with a compression seam. Sometimes the object is a crater rim seen at a grazing angle. Sometimes it's a boulder perched on a slope, made dramatic by a long shadow. Sometimes it is simply a mosaic boundary. The disappearance is not disappointing to science, it is the method working. Some anomalies do persist, and that is where the story stays interesting. Persistent anomalies are usually geologic, like unusual crater chains, impact melt flows, or localized mafic exposures. A crater chain can record secondary impacts from a distant event. An impact melt flow can freeze into lobate shapes that look engineered from orbit. A mafic exposure can mark a deep layer brought up by a single violent strike. Persistence is a clue, but it is not a conclusion. Even then, persistence does not mean intention. It means the moon's processes can produce shapes and chemistry that look surprising when removed from context. The moon is a laboratory for extremes. It preserves ancient surfaces with minimal erosion, so features remain crisp for billions of years. That crispness is visually persuasive. It makes natural geology look like deliberate construction. The far side, more heavily cratered and less resurfaced, preserves that crispness especially well. Now we return to the chapter's core claim. The far side's chemistry is not a single secret ingredient, but a different balance of the same lunar materials. Anorthosite-rich highlands dominate because the flotation crust is more exposed and less resurfaced. Basaltic materials are rarer because thick crust and lower heat budgets limited eruptions. The far side is not a different moon. It is the same moon showing a different layer of its history. Elemental maps reinforce that story through thorium, iron, titanium, and inferred rare earth patterns. The near side carries the strongest creep signature, and the far side carries less of that late-stage residue. That difference is not just academic. It is a constraint on models of lunar formation and evolution. Any theory must explain why one hemisphere kept more incompatible elements near the surface. Any theory must also explain why volcanism favoured one side so strongly. This does not close every loophole because the far side remains undersampled. It does narrow the plausible space for extraordinary claims because independent datasets converge on a coherent natural history. When mineral spectra, elemental maps, and geophysics tell compatible stories, the simplest explanation gains weight. The far side becomes less like a blank canvas and more like a readable text. The remaining mystery shifts from what is it made of to why did it end up that way. The cover-up feeling survives because the evidence is mediated. We do not see raw chemistry with our eyes. We see models, calibrations, and colour scales. We see decisions about bins and baselines. We see uncertainty bands that are rarely shown in social media reposts. That mediation is unavoidable, yet it can feel like a veil. The moon looks close enough to touch, so it feels wrong that we must interpret it through instruments. So the documentary keeps the tension but shifts its target. The mystery is not what is being hidden, but how a small world preserves such a strong hemispheric split. Why did the near side become a landscape of dark lava seas, while the far side stayed pale and high? Why did heat and chemistry concentrate unevenly, and how early did that happen? The far side is not a vault. It is a record, and records invite questions. Chemistry and minerals are one clue, but they are not the only clue people chase. Another is more evocative than any map because it involves signals, silence, and the far side's unique radio environment. On the far side, Earth itself becomes a blocked source, and the sky sounds different. That difference is not a metaphor. It is measurable, and it changes what instruments can do. Next, we move from what the far side is made of to what it lets us hear, and what it blocks. The far side's strangest feature is not a mountain or a crater. It is a condition, radio silence created by geometry and rock. In visible light, the far side is simply unseen from Earth. In radio, it becomes something rarer, a moving shield that can erase a planet's chatter. From Earth, the moon looks like a bright disk with familiar markings. The Maria form dark stains, and the highlands glow pale around them. In radio, that same disk behaves like a barrier with thickness and mass. It blocks a noisy world whose transmitters never truly sleep. Radio Shielding 101 starts with a simple fact. Most human radio transmissions travel in straight lines and spread outward. They do not curve around a horizon the way sound can. Unless a signal is refracted or reflected, it follows line of sight, and the moon is big enough to break that line. At many frequencies, Earth's broadcasts leak into space as a growing bubble. They carry television carriers, radar pulses, aviation beacons, and countless digital harmonics. Some are narrow and steady, like a metronome. Others are pulsed and powerful, like a lighthouse that sweeps the sky. The moon is large enough to interrupt that bubble for anything behind it. When the far side faces away, Earth's direct radio line of sight is cut. The effect is easiest to picture with a clean diagram: Earth radiating outward, the moon sliding in front, and a shadowed region forming behind it. This is not perfect silence, and it is not magic. It is attenuation by bulk rock, plus the absence of direct paths. Lunar regolith and basalt do not absorb every frequency equally, yet across much of the low-frequency band, the moon's sheer thickness forces Earth's strongest signals to fade below detectability. The moon's body blocks most terrestrial radio power by many tens of decibels. What remains is dominated by diffraction around the limb and reflections. Diffraction matters because waves bend, especially at longer wavelengths. A kilometre-scale wavelength can wrap more easily than a metre-scale one, which is why the quiet zone is strongest in the centre. Even so, the far side's central regions are far quieter than any near-Earth orbit. In low Earth orbit, a receiver sees the whole planet in rotation. In higher orbits, it still sees continents, oceans, and a web of transmitters. On the far side, the moon itself becomes the horizon, and that horizon is made of rock. Earth is not the only noise source, and the chapter must name the rest. The Sun emits radio bursts, Jupiter crackles at low frequencies, and the galaxy glows. The sky is never blank at these wavelengths. It is textured with plasma physics, magnetic fields, and the collective hum of charged particles spiraling through space. Even the spacecraft itself can be noisy. Switching power supplies, transmitters, and digital clocks create spurious lines that can masquerade as signals. A warm electronics box can radiate like an accidental beacon. A cable can act like an antenna. In radio astronomy, the instrument is part of the environment, and the environment pushes back. Still, the far side is unique because it removes the loudest nearby contaminant. It is the quietest place near Earth for low-frequency radio astronomy. That quiet is not an aesthetic preference. It is a technical requirement, because the signals of interest are unbelievably faint. Low frequency matters because the most ancient cosmological signals are stretched. The early universe's hydrogen line is red-shifted down into meter and decameter wavelengths. The 21 centimeter hydrogen line begins as a precise frequency in the lab, a quantum transition in neutral hydrogen. Over cosmic time, expansion drags it to much lower frequencies, turning a crisp marker into a distant whisper. Those redshifts correspond to the cosmic dawn and the Dark Ages. They encode when the first stars ignited and when the first galaxies heated hydrogen. Before starlight, hydrogen gas cooled and settled into structure. After starlight, ultraviolet photons and X-rays changed the gas's temperature and ionization, leaving fingerprints in the 21 centimeter spectrum. From Earth, that band is largely inaccessible. The ionosphere blocks and distorts radio waves below roughly 10 to 30 megahertz. It is a charged layer that refracts, absorbs, and scintillates low-frequency signals, especially at night and during solar activity. Even above that, the ionosphere adds phase noise and time variability, turning faint cosmological structure into a moving target. On Earth, radio frequency interference is the other barrier. Human transmitters can be billions of times brighter than the signal cosmologists want. A single over-the-horizon radar can dominate a spectrum. A drifting carrier can paint streaks across an observing band. The problem is not only strength, it is unpredictability. So the far side becomes a scientific promise with a narrative shadow. If it is the best listening post, people assume it is also the best hiding place. That tension is the chapter's engine. Silence invites careful experiments, and silence also invites rumours about what might be heard. To keep the central question alive, we connect silence to asymmetry. The far side is different in geology and chemistry, and it is different in radio environment. A single moon can have two faces in rock and in noise. That duality is real, and it can be exploited without invoking concealment. The documentary's hook returns here in a new form. We never see the far side from Earth, and we also cannot easily hear it. That combination, hidden in light, shielded in radio, feels like narrative gravity. It pulls speculation toward it, even when the physics is straightforward. The first step is defining what quiet means in measurable terms. Radio astronomers describe it as a low background temperature and low interference occupancy. Background temperature is not literal heat. It is a way of measuring radio brightness as if the sky were a warm object, which makes comparisons practical. On the far side, the background is set mainly by astrophysical sources. Galactic synchrotron emission dominates at very low frequencies. It comes from electrons spiraling in magnetic fields, producing a smooth, steep spectrum that brightens dramatically as frequency drops. That emission is loud, but it is predictable and smooth, which makes it mathematically tractable. It can be modelled and subtracted, unlike human-made interference that spikes and drifts. Human signals have edges, harmonics, and sudden on-off behaviour. They also change with politics and infrastructure. A new transmitter can appear overnight, while the galaxy keeps its schedule. A far-side observatory could search for the global 21 centimeter signal. It could also attempt interferometry to map fluctuations across the sky. Those goals require stable calibration and long integration. They also require that local electronics be disciplined, shielded, and quiet, because a tiny ripple in the instrument response can look like a cosmological feature. This is where perfect silence becomes a misleading phrase. The far side is quieter than anywhere nearby, but it is not empty of radio phenomena. Space plasma produces natural radio emissions. The solar wind interacts with magnetic fields and creates bursts, hiss, and drifting tones that can sound almost musical when converted to audio. The Moon has no global magnetic field, but it has crustal magnetism in patches. Those anomalies can shape local plasma environments. They can deflect particles, create mini magnetospheres, and alter the way electric fields form near the surface. In radio terms, they can change the local noise floor in ways that depend on solar wind conditions. The lunar wake also matters. As the solar wind flows past the moon, it creates a downstream cavity and boundary regions. The wake is not a simple shadow. It is a dynamic region where density drops, particles stream in, and electric potentials can build. Electrons and ions can generate waves at those boundaries, and a receiver can record them as broadband noise or narrowband features. So when people report unusual signals near the moon, we need categories. Some are natural plasma effects, some are reflections, and some are instrument artifacts. Instrument artifacts are the most common and the least intuitive. A receiver can create its own lines through mixing, aliasing, and intermodulation, especially when strong signals leak into nonlinear components. A strong transmitter on the spacecraft can leak into the science channel. A digital clock can create combs of evenly spaced spikes. Even temperature changes can matter, because oscillator frequencies drift with heat. In the cold, shadowed parts of a lunar orbit, a system can behave differently than it did during ground tests. Reflections are the next category, and they are often misunderstood. A signal can bounce off the lunar surface or off the spacecraft structure. The lunar surface is rough at many scales, so reflections can be specular in places and scattered in others. A reflection can shift phase and create patterns that look like modulation, and it can also create delayed echoes that resemble a second source. Genuine astrophysical sources are real and sometimes dramatic. Solar radio bursts can saturate receivers and produce sweeping features. These bursts are tied to flares and coronal mass ejections, and they can evolve in seconds. Jupiter's decametric emission is another classic source. It is intense at low frequencies and can be detected far from Earth, often modulated by the motion of its moon EU. Pulsars can also be detected, though they are faint at very low frequencies. Their periodicity is a strong test for whether a signal is real. If a feature repeats with a known pulsar period and appears in the expected sky direction, it becomes less mysterious. If it appears only once, in one channel, during a thermal transient, it becomes more suspicious in the ordinary engineering sense. With those categories in place, we can address the rumour layer without feeding it. The far side has been linked to stories of strange transmissions for decades. Historically, the most cited claims cluster around early lunar missions and the Cold War. They often rely on partial transcripts, second-hand anecdotes, and missing context, which is exactly the recipe for durable myth. One recurring narrative claims that astronauts heard music or voices on the far side. The verifiable record shows mostly routine communications and occasional audio artifacts. In analog systems, heterodynes can produce tones. In voice circuits, squelch and carrier dropouts can create warbles. A human brain is built to find patterns, even in noise. Apollo communications did drop out behind the moon, and that gap is important. The blackout is expected because line of sight is blocked. During those minutes, the public heard nothing, and that silence became a canvas. Later retelling sometimes filled it with invented content, because a gap feels like an invitation. There were also genuine mystery moments in early space radio. Tracking stations sometimes heard unexpected tones, but later analysis often traced them to equipment. Receivers drifted, ground stations had local interference, tape recorders introduced artifacts. The early space age was a triumph of engineering, but it was also an era of imperfect instrumentation. Soviet and American programs both used multiple frequencies and modulation schemes. Crosstalk and harmonics could be misinterpreted by outside listeners. A strong signal on one band can produce a weaker ghost elsewhere. A poorly documented monitoring setup can turn that ghost into a story. The far side also complicates independent verification. If a signal is heard by a spacecraft behind the moon, Earth-based receivers cannot confirm it directly. That asymmetry is technical, but it feels political. It creates a one-way window where only the mission team has the full dataset, including the calibration context that makes sense of anomalies. This is where the cover-up narrative finds oxygen. Limited access to raw telemetry can look like deliberate withholding, even when it is bandwidth and prioritization. Deep space links are finite, antenna time is scheduled, science data competes with engineering health data, and the system is designed to keep the spacecraft alive first. We should be explicit about what is verifiable. Mission archives contain many radio science datasets, navigation logs, and engineering telemetry. They show expected blackouts, expected relay operations, and expected noise. They also show that most signals are either known sources or system behaviour, which is less thrilling but far more consistent. What remains speculative is narrower than the rumours suggest. It includes ambiguous detections at the edge of sensitivity and unrepeatable events. Unrepeatable events are not automatically suspicious. In radio, transient interference can be local, and transient astrophysical bursts can be rare, especially when the sky is dominated by variable solar activity. The question is whether an event can be reproduced or cross-checked. Without that, the correct label is unknown, not hidden. Scientists live with unknowns, but they do not promote them to conclusions. They build procedures that slowly shrink the space where mystery can hide. Now we pivot to the engineering constraint that shapes everything on the far side. If Earth cannot see a far-side lander, it cannot talk to it directly. That is why far-side missions require relay satellites. They place a communications node where it can see both Earth and the far side, turning a blocked line into a bent path. The most common geometry is a halo orbit around Earth, Moon L2. L2 sits beyond the Moon, roughly along the Earth, Moon line. It is not a physical object, but a gravitational balance point where a spacecraft can orbit with modest station keeping. In visuals, it's often drawn as a small loop behind the Moon, an invisible perch with a clear view. A relay near L2 can maintain line of sight to Earth and to a far-side surface site. It can pass commands down and send data back. The relay's antennas track Earth while also listening to the lander, and its onboard systems manage timing so packets do not collide. China's Queqiao relay for Chang'e 4 made this architecture famous. It demonstrated sustained far-side operations with a dedicated communications bridge, proving that the far side is not unreachable, only indirect. Relay satellites also support navigation and timing. They provide a stable link budget and allow higher data rates than a weak indirect path. They can also carry their own science payloads, quietly measuring the radio environment while they perform their primary job. In a sense, the relay becomes both messenger and witness. But relays create a second layer of infrastructure that the public rarely sees. A lander, a rover, and a relay form a network that feels like a closed system. That closed system fuels secrecy narratives in predictable ways. People imagine the relay as a gatekeeper that can filter what is sent back, because it is literally the only route home. In reality, filtering is often mundane. Missions compress images, prioritize health telemetry, and downlink science in scheduled windows. They also manage limited power and thermal cycles. A far-side night lasts 2 Earth weeks, and survival strategies can reduce communications, leaving long stretches where nothing arrives and imaginations rush in. Still, the perception problem is real. The far side already feels hidden, and a relay makes the hiding feel engineered. We address that by separating capability from intent. A relay enables communication, and it also creates a single choke point for data flow. A choke point can be audited if raw data is released and independently processed. It cannot be audited if only curated products appear. So transparency becomes part of the story's resolution. The more missions publish raw radio spectra, calibration files and processing steps, the less room rumors have. Raw data is not automatically understandable, but it is checkable. It allows independent teams to look for instrument signatures, compare with space weather, and test alternative explanations. Now we return to cosmology, because it is the strongest scientific reason for far-side radio quiet. The far side is not only a shield, it is a laboratory. The cosmic dawn signal is expected to be a faint absorption or emission feature against a bright foreground. Extracting it requires extreme control of systematics, because the foreground is not a nuisance, it is the dominant thing in the measurement. Foregrounds are thousands of times stronger than the target. Galactic synchrotron emission varies smoothly with frequency, but instruments imprint ripples. Those ripples can come from cable reflections, ground coupling, and beam chromaticity, where the antenna pattern changes with frequency. In plain terms, the instrument can accidentally paint a fake feature onto a smooth sky. That is why far-side experiments emphasize antenna stability and thermal control. A metal antenna expands and contracts with temperature swings. Electronics drift as they warm. Even the lunar surface beneath an antenna can change its effective impedance. On the far side, the thermal environment is harsh, so the engineering must be deliberate. Earth-based experiments like EDGES and others have attempted global signal detection. Their controversies show how hard it is to separate sky from instrument. A far-side sight reduces one major contaminant, but it does not remove the others. It reduces human interference, not the need for rigorous calibration, careful modelling, and skeptical analysis. This is where the chapter's title earns its second half. Perfect silence is a myth, but unusual signals are a certainty if you listen long enough, so we define unusual with discipline. Unusual can mean a transient burst, a narrow-band line, or a pattern inconsistent with known sources, and each type triggers a different checklist. Then we state how scientists triage such events. They check whether the feature tracks the spacecraft, the antenna orientation, or the sun. They check whether it appears in multiple receivers or polarizations. They check whether it repeats at the same sidereal time, which would suggest a sky-fixed origin rather than a local one. They compare with space weather data, solar radio monitors, and plasma instruments. They look for correlations with known interference modes, like transmitter duty cycles or power system switching. Only after those checks does an event become a candidate astrophysical transient. Even then, it is a candidate until another instrument confirms it, because radio astronomy is strongest when it is redundant. Rumours invert that process. They start with the conclusion and treat the lack of confirmation as proof of suppression. The documentary's job is to keep the mystery while restoring the method. The far side is a place where the universe is easier to hear, not easier to fake, and that distinction matters. We also need to acknowledge the historical record of signals tied to the moon. Some early probes reported unexpected noise during occultations. Occultation is when the moon blocks a radio source, and the signal drops. That drop can reveal the source size and the plasma along the path, turning the moon into a knife-edge experiment. In some cases, the drop was not clean. Scattering and diffraction created fringes that looked like extra structure. Those fringes are real physics, not messages. They are the wave nature of radio interacting with a sharp lunar limb, producing interference patterns that can be predicted once geometry and wavelength are known. There are also reports of lunar radio emission that confuse audiences. The moon emits thermal radio, reflecting its surface temperature, and that emission changes subtly with the lunar day. It also reflects Earth's radio leakage on the near side. That reflection can be detected as a weak echo, especially at certain frequencies, which makes the moon a passive mirror for our own noise. On the far side, that reflected component is largely absent. That absence is part of the quiet, and it is measurable. It is not a philosophical quiet. It is a spectrum with fewer artificial lines, a baseline that sits lower, and a time series that behaves more like a natural sky. Another class of claims involves backscatter from radar experiments. Powerful radars on Earth have bounced signals off the moon for decades. Those experiments can create echoes and Doppler shifts that are precisely predicted, because the moon's motion is known to high accuracy. Misreadings often come from not knowing the transmission schedule, or from encountering an echo without the context that produced it. So we state the boundary between verifiable and speculative. Verifiable includes shielding, blackouts, relay necessity, and known natural radio sources. Speculative includes unconfirmed transient detections without raw data, and narratives built from gaps in public audio. The line between them is not cynicism, it is documentation. We also admit what we do not yet have. We do not have a mature, long-lived far-side low-frequency array operating for years. We have concepts, prototypes, and short-duration instruments. We have orbital measurements and radio environment surveys, which are valuable but incomplete. The far side remains under-instrumented compared with its promise. That under-instrumentation is a scientific gap, not a deliberate silence. Now we connect back to earlier chapters' theme of undersampling. Just as far-side rocks are scarce, far-side radio datasets are limited, and limited data always leaves room for competing stories. That limitation leaves loopholes for both science and speculation. Science sees it as motivation for new missions, and rumour sees it as missing evidence. A key beat is that radio quiet is not only about hiding from Earth, it is about hearing the early universe at frequencies Earth cannot access, which reframes the far side as outward-looking rather than inward-looking. That payoff is concrete. A detection of the global 21-centimetre signal would constrain the first star formation and the timing of reionization. It would also test models of early heating by X-ray sources and black holes. It would anchor a timeline that currently relies on indirect probes, like the cosmic microwave background and high redshift galaxies. So the far side becomes a bridge between lunar exploration and cosmology. A cratered hemisphere turns into an observatory platform. In visuals, imagine a simple antenna array laid across grey regolith, with Earth hidden below the horizon and the Milky Way arcing overhead. The scene feels quiet, but the receiver is busy, counting photons that have travelled for billions of years. But an observatory platform requires landing, deploying and surviving. That brings us to the next step in the documentary's arc. If the far side is the best listening post in near-Earth space, the next step is going there deliberately. We have to land, build and measure, and we have to do it in a place where every message home must pass through a relay. That landing story is where secrecy narratives intensify, because surface operations create images, panoramas, and long-duration datasets. It is also where the scientific record becomes harder to dismiss, because instruments can be calibrated on site and checked over time. Repetition is the antidote to rumour. A single strange event can be a story, but a stable dataset becomes evidence. So we end with a controlled escalation. Silence is not a void, it is a resource, and resources attract both science and suspicion. Next, we follow the missions that actually touch the far side. We track what they sent back, what they could not send directly, and what changed afterward. The far side stops being an idea when a spacecraft must survive there, because survival turns speculation into engineering. Orbit can suggest patterns, but landing forces a verdict on terrain, temperature, and truth. On the near side, missions fail loudly and quickly, with antennas still pointed toward Earth. On the far side, they can fail silently, because Earth cannot hear them directly, and silence can look like mystery. A far side landing begins with a basic problem of geometry, and geometry does not negotiate. The Moon blocks line of sight, so a lander cannot talk to Earth without help. Every command, every image, every heartbeat packet must bounce through a relay, and the path is fragile. The relay is not optional infrastructure, it is the mission's only voice, its throat, its ears, and its only witness. Most relays sit in carefully chosen orbits that keep both Earth and the far side in view, often near the Earth, Moon L2 region. From that distant perch, the relay watches the lunar limb like a tightrope walker, maintaining a constant angle that keeps the link alive. Small errors in station keeping accumulate, and fuel spent correcting them is fuel not available for extended operations. Even the radio spectrum matters, because higher frequencies carry more data, but demand tighter pointing and cleaner margins. That dependence changes engineering culture in ways the public rarely sees. Teams design for delays, dropouts, and narrow windows of contact because the relay's orbit and antenna geometry set the schedule. They plan for autonomy when the link goes quiet, because it always will at some point. If the lander panics, Earth cannot immediately intervene, and the far side punishes hesitation with irreversible momentum. In practice, autonomy means a stack of software behaviours that must be trusted under stress. Fault protection rules decide when to stop a motor, when to reboot a computer, and when to wait for instructions that cannot arrive. The lander must distinguish a real problem from a transient glitch, which is harder than it sounds. A single flipped bit from radiation can imitate a sensor failure, and the wrong response can waste precious fuel. Terrain is the first hard constraint, and it is harsher than the near side's famous plains. Farside highlands are older, more cratered, and more blocky at many scales, because they were not resurfaced by widespread basalt floods. In orbital light, the highlands look pale and uniform, yet the ground is a mosaic of shattered rock. Slopes hide in shadows, boulders cluster in ejecta, and crater rims create sudden relief that can tilt a vehicle in seconds. A safe ellipse on paper can contain one lethal rock, and the lander only learns that at the end. As the descent camera sharpens, the surface resolves into overlapping craters, bright ejecta rays, and angular blocks that cast knife-edged shadows. The far side's texture is visual noise, and the guidance system must find order inside it. Hazard maps are built from orbital images, but the final meters are decided by what the lander sees in real time. Navigation is the second constraint, and it is less forgiving without Earth in the sky. Near-side landers can use direct tracking and continuous ranging, with multiple stations refining the trajectory. Far-side landers must rely on relay-based ranging and onboard hazard detection, which introduces latency and reduces redundancy. That pushes more decision-making into software, where uncertainty becomes a design parameter rather than an afterthought. During descent, the spacecraft fuses inertial measurements with optical cues, matching live images to onboard maps. This terrain relative navigation is powerful, yet it depends on lighting and recognizable landmarks. A low sun can exaggerate shadows and confuse feature matching, while a high sun can wash out contrast. The moon's surface is not painted for cameras, so the algorithms must cope with glare, darkness, and the deceptive simplicity of grey dust. Thermal extremes are the third constraint, and they shape every subsystem from the battery to the bolts. 2 weeks of sunlight can overheat electronics and bake batteries, especially when radiators face a bright, airless landscape. 2 weeks of night can freeze lubricants and starve solar power, turning survival into a slow accounting problem. Survival requires heaters, insulation, and strict energy budgets that compete with science, because every watt has a job. Thermal design is also about time constants, the lag between environment and hardware. A metal chassis can store heat like a reservoir, smoothing swings, but it can also trap heat where it is unwanted. Multi-layer insulation reflects radiation, yet it complicates cooling during the day. Even dust matters, because it changes surface emissivity and can blanket radiators, quietly altering a thermal model that looked perfect on Earth. Even the descent profile changes under these constraints, because the far side demands both precision and restraint. A far side lander must manage fuel, timing, and attitude while also protecting antennas and instruments from plume debris. It must land upright, because the relay link assumes a working geometry and a clear antenna view. A tilted lander is not only unstable, it is potentially mute, alive, but unable to tell anyone. This is why far-side touchdowns are rare and politically meaningful, even when the science is the headline. They are demonstrations of guidance, navigation, and control under isolation, where the final decisions happen beyond direct human reach. They also create a new kind of evidence, because surface measurements can validate or embarrass orbital interpretations. The far side becomes measurable in the most literal sense, with numbers that come from contact, not inference. Historically, the far side was once a blank in human imagination, then a shock when the first images arrived. Early lunar probes revealed a hemisphere dominated by battered highlands, with fewer dark maria than the near side. That asymmetry raised questions about crustal thickness, internal heat, and the moon's earliest differentiation. Each new dataset sharpened the puzzle, but only a landing could test it where it mattered, at the scale of rocks and grains. Now we move from the silence of radiogeometry to the noise of contact with soil. The first scoop of regolith is not symbolic, it is calibration, and calibration is the beginning of trust. Orbital maps infer chemistry through photons and particles, integrating signals across wide footprints. A lander measures the ground as matter, with instruments that can be checked against known standards and repeated until the uncertainty is visible. In situ chemistry begins with elemental composition of the regolith, which is both a surface and a history. Spectrometers on the surface can measure X-ray fluorescence or other signatures triggered by sunlight and energetic particles. They can estimate major elements like silicon, aluminum, calcium, iron, and titanium, which define the broad families of lunar rocks. They can also constrain trace elements that orbiters see only in broad averages, where local anomalies disappear. The physics is straightforward, even if the hardware is delicate. Incoming radiation excites atoms in the soil, and those atoms emit characteristic energies as they relax. By counting those energies, the instrument reconstructs a chemical fingerprint, yet the signal depends on grain size, viewing geometry, and surface roughness, so the lander must measure context as well as composition. The key is scale and context, because scale determines what a map really means. Orbital gamma-ray pixels can span tens of kilometers, blending units into one value that looks clean on a screen. A lander samples centimeters to meters, and it can repeat measurements across a small traverse. That repetition reveals heterogeneity, mixing, and the effects of space weathering on the topmost grains, where solar wind and micrometeorites do their quiet work. Microscopic imaging is another ground truth that orbit cannot replace, because it reveals the architecture of dust. Cameras that resolve grains show shape, glass content, and agglutinates formed by micrometeorite melting and welding. Under magnification, the regolith becomes a field of sharp fragments and glossy beads, each one a tiny impact story. Grain size affects reflectance and spectral band depth, which can mimic compositional change from orbit, So a microscope turns ambiguity into a physical explanation. Space weathering is not just a buzzword, it's a chemical and optical transformation. Solar wind implants hydrogen and helium into grain rims, while micrometeorite impacts vaporize and redeposit material as nanophase iron. Those changes darken and redden spectra, making fresh rock look older in light alone. When a lander compares a bright, newly exposed patch to mature soil nearby, it watches the moon's surface chemistry in motion. Regolith mechanics also matter, because the soil is a record and a hazard at the same time. Penetrometers and wheel sinkage reveal bearing strength and cohesion, which determine whether a rover glides or bogs down. Those properties control drilling feasibility, sample acquisition, and even the stability of a parked lander during thermal cycling. They also inform how impacts garden the surface, which affects how deep a sample must go to escape mixing and reach older material. The moon's regolith is not a uniform powder, and that surprises people who imagine a simple dust layer. It can be fluffy at the top, compacted beneath, and laced with buried rocks that strike a drill like hidden teeth. Electrostatic charging can make fine grains cling to surfaces, especially near terminators where sunlight and shadow meet. Every mechanical measurement becomes a clue to the environment that future missions must live with. Ground-penetrating radar adds a third dimension, and it is central to far-side claims because it sees what light cannot. Radar from a rover can profile layers beneath the surface, mapping buried ejecta, regolith thickness, and possible basalt flows that never broke the surface. It can detect changes in dielectric properties that imply rock abundance, layering, or blocky deposits. It cannot identify a hidden base by itself, but it can falsify simple stories by revealing whether the subsurface is orderly or chaotic. Interpreting radar is an exercise in humility, because reflections can lie without context. A strong reflector might be a boundary between fine regolith and blocky ejecta, or it might be a change in porosity. Multiple passes, different frequencies, and correlation with surface geology helps separate possibilities. When radargrams are overlaid on Traverse maps, the far side gains depth, turning a flat panorama into a layered archive. Seismology is the instrument people expect, and the one the far side still lacks at scale. A single seismometer can detect impacts, thermal cracking and deep moonquakes, which are faint but persistent. A network can locate events, map crustal thickness, and constrain mantle properties through wave speeds and attenuation. On the far side, seismology would directly test models of asymmetry, because it measures structure rather than surface colour. The concept is straightforward, and the implementation is brutal, because the moon is quiet in the wrong ways. Seismometers need stable coupling to the ground, and protection from thermal swings that can mimic signals. They need long duration to accumulate events, especially on a body with limited tectonic activity. They also need precise timing and data return through the relay, which makes bandwidth a scientific constraint rather than a convenience. A far-side seismic station would also face a subtle advantage that becomes a theme. With Earth's radio noise blocked, sensitive instruments can operate in a cleaner electromagnetic environment. That quiet is not absolute, but it is meaningful, and it changes what can be measured. The far side is isolated, and isolation can be both a threat and a gift. This is where South Pole, Aitken returns as the chapter's scientific target, looming like a scar across the lunar globe. It is the largest and oldest accessible basin, and it may have excavated deep material during a violent early epoch. If the impact punched through the crust, it could have exposed lower crust or upper mantle components. That would turn a far-side landing into a probe of lunar interior evolution, not just a surface survey. From orbit South Pole, Aitken is a basin of subtlety rather than spectacle. Its rim is degraded, its floor is complex, and its mineral hints are scattered across a vast area. The basin's age means it has been overprinted by later impacts, mixing deep and shallow materials like a stirred sediment. The challenge is to find places where the deep story still peeks through, perhaps in central peaks or fresh crater walls. The basin also matters for chronology and the late heavy bombardment debate, because time is the moon's most valuable export. If there was a spike around 3.9 billion years ago, basin melt should record it in their radiometric clocks. If impacts declined smoothly, ages should spread differently across basins, and the spike becomes a mirage of sampling. Orbital crater counts are suggestive, but they are not absolute time without samples, and the far side is where the timescale is weakest. So the far-side landing agenda becomes clear, and it is as much about dates as it is about rocks. Find impact melt sheets, date them, and compare to near-side basins that anchor existing models. Identify deep origin lithologies and test whether mafic signatures are mantle or later volcanism. Replace model ages with radiometric ages and close the loophole that undersampling created because ignorance loves empty space. But landing in South Pole, Aitken is not like landing on a Mare Plain, where wide basalt flats forgive small errors. Slopes are steeper, illumination is complex, and shadows persist near the poles, stretching like ink across the terrain. Power planning becomes a geometry problem, not just a battery problem, because sunlight arrives at angles and disappears behind ridges. A rover route becomes a thermal schedule, because shade can be both refuge and trap. In the visuals, the sun hangs low, and the landscape becomes a high-contrast engraving. Crater rims glow while floors vanish into black, and boulders throw shadows longer than the rover itself. The horizon is crowded with overlapping relief, making distance hard to judge. Every meter forward is a negotiation with light, heat, and the limits of traction. This is why mission planners lean on orbital reconnaissance, yet still accept residual risk as the price of discovery. High-resolution cameras map boulders and slopes, but they cannot see every hazard hidden by angle or dust. Laser altimetry provides elevation models, but small rocks remain below its grid, waiting like caltrops. The far side forces humility, because the last meters are always a surprise, and surprise is where accidents live. When a mission succeeds, the payoff is not only images, even though images are what the public remembers. It is the ability to compare orbital predictions to ground measurements, pixel by pixel in meaning rather than in colour. If an orbiter inferred low titanium, the lander can confirm it in soil and quantify the error. If a spectral anomaly suggested olivine, a microscope and spectrometer can test the claim and constrain how it got there. The far side becomes less interpretable and more accountable, and accountability is a scientific virtue. Models are allowed to be wrong, but they must be wrong in ways that teach. A landing site becomes a calibration point for the entire hemisphere, tightening uncertainties in global maps. Over time, multiple sites turn the far side from a single mystery into a set of constrained hypotheses. A key example is the first sustained far-side rover operations enabled by a dedicated relay, which changed what reachable meant. The relay architecture proved that long-duration science is possible without direct Earth contact, even with narrow windows and careful scheduling. It also proved that the far side is not unreachable, only indirect, and indirectness is not the same as secrecy. That indirectness is exactly what conspiracy narratives exploit, so the data trail matters and the chain of custody matters. On the ground, instruments can also test space weathering in real time, rather than treating it as an abstract correction factor. They can compare fresh ejecta to mature soil and quantify how quickly optical properties change under local conditions. They can measure how solar wind implantation differs with local magnetic anomalies, where fields can deflect particles and create patchy weathering. These details feed back into remote sensing models, improving global maps that once looked like guesswork. Farside landers also reveal how deceptive lighting can be, and how quickly perception becomes narrative. A boulder field can look smooth at high sun and lethal at low sun, when shadows hide gaps and edges. A ridge can look like a wall when shadows stretch, then vanish when illumination changes and contrast collapses. Surface panoramas across multiple times of day become a direct antidote to pareidolia, because they show the same place telling different visual stories. Now we address the most sensitive part of the story. How does far-side data become public, and why do delays happen, especially when the mission feels distant already? The public often sees only curated images and summary plots, which feels like a filter placed between reality and curiosity. In reality, missions generate layered products, and each layer has its own timeline, its own quality checks, and its own gatekeepers. The pipeline starts with raw telemetry, and raw means messy rather than meaningful. Bits arrive through the relay, then through ground stations, then into mission operations centers where they are sorted and validated. Engineers first check spacecraft health, because a dead rover produces no science and no future. Science teams then reconstruct files, apply time tags, and verify that packets are complete, because missing packets can distort measurements. Calibration is the next delay, and it is not cosmetic even when it looks like paperwork. instruments drift with temperature, radiation, and aging, and those drifts can masquerade as discovery. Flat fields change, detector gains shift, and background levels vary with cosmic rays that spike unpredictably. Teams must correct these effects before measurements can be compared across days, sites, and instruments. Otherwise, trends are just instrument mood. Geolocation is another hidden labour, and it is where images become maps. A spectrum is only meaningful if you know exactly where it was taken and what it sampled, down to the meter. Rovers slip, wheels sink, and odometry accumulates error, especially on slopes and loose soil. Teams fuse camera images, inertial data, and sometimes orbital tie points to build a traverse map, and that reconstruction can take months. That process can change interpretations, which is why it is slow on purpose. A measurement that looked like a compositional boundary might become a lighting artifact once the geometry is corrected. A radar reflector might align with a buried crater rim only after the route is refined. The far side is not only hard to reach, it is hard to register accurately, and registration is the difference between story and science. Then comes the scientific publication layer, where results are forced to survive criticism. Teams write papers, submit to peer review, respond to critiques, and revise methods until the uncertainties are explicit. Peer review is slow because reviewers demand error bars, not excitement, and because extraordinary claims require ordinary rigour. The result is less cinematic, but it is the mechanism that turns mission claims into community knowledge. Archives are the final layer, and they are where independent verification becomes possible, which is the antidote to rumour. Space agencies maintain repositories for images, spectra, and derived products, often with standardized formats and documentation. Some data is released quickly, some after proprietary periods that reward instrument builders who spent years developing hardware. Proprietary windows are common in planetary science, but they look like secrecy to outsiders who do not see the bargain. National security boundaries add another complication, especially for dual-use technologies that overlap with terrestrial capabilities. High-resolution imaging, precise navigation methods, and certain communications details can be sensitive, even when the science is benign. Agencies may redact or delay specific metadata while releasing science results, separating what is measured from how it is measured. That boundary is real, and it feeds suspicion because it is rarely explained clearly. There are also mundane reasons for gaps that become myths, because humans prefer plots to logistics. Bandwidth is limited, so teams downlink thumbnails first and full frames later, prioritizing situational awareness over beauty. Power is limited, so science pauses during thermal survival, and instruments are warmed slowly to avoid damage. Dust can cover optics, and a camera can be deprioritized to save energy for mobility, so a missing day of images can be a battery story. Still, the far side's relay dependence creates a perception problem that near-side missions rarely face. One choke point carries everything, and outsiders cannot listen in directly with backyard antennas and patience. That makes transparency practices more important, not less, because trust must be built with process rather than proximity. Releasing raw data, calibration files, and processing code is the clearest way to shrink the rumour space, and it invites the public into the method. Now we return to the central question with new leverage, because we have moved from theory to measurement. The far side is different because its crust is thicker, its surface is older, and its heat budget was lower, at least according to current models. Landers can test these claims by measuring composition, regolith properties, and local geology, where the models make predictions. Sample return can test them decisively by dating rocks and identifying deep origin minerals that cannot be faked by lighting. Sample return is the turning point because it breaks the near-side bias that has shaped lunar science for decades. Apollo and lunar samples anchored our lunar timescale, but they came from a limited province with its own volcanic history. Far-side samples would recalibrate crater count chronologies across the whole moon, tightening ages for surfaces we have only counted. They would also test whether South Pole, Aitken contains mantle signatures or only mixed crustal debris, which decides how deep that ancient impact reached. Planning a far-side sample return is a chain of hard steps, where each success depends on the last. A lander must collect, seal, and preserve material without contamination, because Earth's air and moisture can alter delicate phases. An ascent vehicle must launch from an uneven surface into a precise trajectory, guided by inertial systems that cannot be corrected in real time. A relay must support critical phases, and an orbiter must rendezvous and capture, and each link is a failure point. Each link also produces data that can be audited, which matters in a story haunted by distance. Telemetry logs show motor currents, valve timings, and trajectory solutions, and those numbers are hard to romanticize into myth. The sample container has seals, witness plates, and documented handling procedures because provenance is the soul of geology. If the far side is to become a laboratory, it must also become a paper trail. Even before return, in situ dating concepts are emerging as a partial solution, especially when return is years away. Instruments could estimate ages through isotopic measurements on the surface, though with larger uncertainties and stricter assumptions. That would still constrain models and guide which samples matter most, narrowing targets in a vast basin. It would also reduce the temptation to treat every anomaly as unknowable, because approximate time is better than timeless speculation. The far side, once called hidden, becomes a place where uncertainty is quantified rather than dramatized. A rover traverse becomes a set of coordinates, spectra, images, and radargrams that can be cross-checked by different teams. A crater wall becomes a stratigraphic section, not a silhouette, with layers that can be described and compared. The mystery does not disappear, but it changes form, from speculation about concealment to questions about origins. Now we raise the stakes toward the climax. On-the-ground exploration does not only answer what the far side is made of, or how old its scars are, it also points to what the far side might hold in its coldest shadows, where physics becomes a vault. Near the poles, some craters never see sunlight, and their floors can trap volatiles for billions of years, untouched by the daily cycle that erases evidence elsewhere. This possibility is not science fiction. It is thermodynamics and orbital geometry, expressed in temperature curves. Permanently shadowed regions can stay below the sublimation temperatures of water ice and other volatiles, because sunlight never arrives to provide energy. Hydrogen signals from orbit hint at enrichment, but ground truth is needed to separate ice, hydroxyl, and implanted hydrogen in minerals. The far side's polar terrain makes that test harder and more valuable, because access itself is an experiment. In the visuals, those shadowed craters look like holes cut into the world, blacker than the sky. The rim is sunlit and sharp, while the interior is a cold well where instruments must bring their own warmth. A rover's headlights vanish into darkness, revealing only a few meters of powder and rock. What lies beyond that edge is not supernatural, but it is unknown in the most practical way. Volatiles change everything about future presence, because they turn exploration into infrastructure. Water can support life support, radiation shielding, and propellant production, and each use reduces what must be launched from Earth. If ice exists in accessible quantities, a base becomes more than a flag and footprints, because it can refuel and expand. It becomes an industrial foothold, and the far side's radio quiet adds strategic scientific value for sensitive measurements. That is why the far side's shadows feel haunting in this story, even when the science is sober. They are places where sunlight never reaches, where instruments must work without warmth, and where resources may be locked in darkness. They also intensify the cover-up instinct because what cannot be seen invites stories that feel like explanations. The correct response is the same as before: land, measure, publish, and let independent eyes check the work. So the chapter ends on a controlled pivot from touchdown to consequence. Touchdown turns the far side from a map into a site, and a site into a plan, with constraints that can be priced and engineered. The next question is no longer whether the far side can be reached, because reach has been demonstrated under isolation. The next question is what we will build there, and what the cold shadows will force us to become. The far side has always invited the same suspicion, because what we cannot see feels like an invitation to imagine. If we cannot see it, then something must be there, waiting behind the limb where telescopes and intuition both lose their grip. This chapter follows the strongest claim that stays anchored to evidence, even when the mood turns mysterious. Not alien structures, not hidden transmitters, not a secret city under glass. A resource that can hide in plain physics, water ice and other volatiles trapped in permanent shadow near the poles. The moon's poles are different because the moon barely leans, and that small fact changes everything about light. Its axial tilt is only about 1.5 degrees, so sunlight skims the polar horizons like a low flashlight beam. At mid-latitudes, the sun rises high and bakes the surface, but near the poles, crater rims and ridges can block sunlight forever. Permanent shadow is not a poetic phrase, and it is not a seasonal metaphor. It is a geometric condition created by low tilt and rough topography, where the sun's path never climbs high enough to clear local relief. A deep crater near the pole can keep its floor in darkness through every season, because the rim stays taller than the sun. Imagine the camera drifting over a polar landscape of broken rings and knife-edge ridges, where bright peaks glow while adjacent hollows remain ink black. The boundary between light and darkness can be sharp, almost theatrical, because there is no atmosphere to soften it. In some places, the sun grazes a rim at a shallow angle, and the shadow stretches like a permanent eclipse. Temperature follows sunlight, and the moon has no air to share heat from one place to another. Sunlit regolith can swing from hot daytime to cold night quickly, because the surface is a poor conductor and radiates heat straight to space. In shadow, the energy budget collapses to faint scattered light and weak thermal radiation, and some crater floors settle into extreme cold. These places are called cold traps because they trap molecules, not because they trap light. In the coldest regions, temperatures can stay below roughly 40 to 100 Kelvin, which is colder than Antarctica by a wide margin. At those temperatures, water ice is stable against sublimation for immense timescales, and other volatiles can also persist depending on their vapor pressures. A cold trap is a vault made of thermodynamics, and it works without walls or locks. If a water molecule lands there, it loses energy and sticks to grains or existing ice, like breath freezing on metal. If it tries to escape, it must gain enough heat to sublimate, and with no direct sunlight, that heat rarely arrives. The stability is not just about cold, but about how cold varies with time. A surface that warms briefly above a critical threshold can drive molecules off, even if it refreezes later. That is why scientists model not only average temperature, but peak temperature, microillumination, and the slow seep of heat through regolith. Over billions of years, the moon has been bombarded by sources of volatiles, and the record is written in impacts and dust. Comets and hydrated asteroids deliver water and carbon-bearing compounds, sometimes as ice, sometimes locked in minerals, sometimes as organics. Micrometeorites bring small but steady contributions, and the solar wind implants hydrogen into the surface atom by atom. The far side is not uniquely favoured for ice by sunlight alone, because both poles share the same tilt and the same basic geometry. Yet the far side's polar terrain and exploration constraints matter in practice, because what is hard to reach is also hard to measure. Far-side polar cold traps are harder to verify from orbit and harder to sample on the ground, and that difficulty becomes part of the cover-up story even when the physics is ordinary. We cannot simply look into a shadowed crater and see ice, at least not the way we see frost on Earth. Visible cameras see darkness, and even infrared struggles when surfaces are near absolute cold and emit little thermal radiation. So the evidence comes from indirect detection, and the method is the message because the message is probabilistic. First, neutron suppression, which sounds abstract until you picture the surface being constantly struck by invisible bullets. Galactic cosmic rays slam into the lunar regolith and trigger spallation, knocking neutrons out of atomic nuclei like chips from stone. Those neutrons leak back into space, where orbiters can count them as a kind of planetary radiation signature. Hydrogen is special because it slows neutrons efficiently, almost like a cushion in a pinball machine. When neutrons collide with hydrogen nuclei, they lose energy quickly because the masses are similar. If hydrogen is present in the regolith, fewer high-energy neutrons escape, and detectors see a measurable dip. So a dip in epithermal neutrons becomes a proxy for hydrogen enrichment, and that proxy can be mapped across the poles. It does not prove water by itself, because hydrogen can exist as hydroxyl, implanted protons or hydrated minerals. Yet at the poles, hydrogen plus permanent shadow becomes a strong clue, because the cold trap provides a storage mechanism that makes accumulation plausible. Neutron maps have limits that matter for trust, and those limits are easy to misunderstand when the map looks crisp. Their footprints can be tens of kilometers wide, blending cold traps with sunlit slopes and averaging over complex terrain. A strong signal can mean concentrated ice in small patches, or diffuse hydrogen mixed through soil, and the data does not hand us a clean picture. That ambiguity is where narratives grow, because humans dislike probabilities when stakes feel strategic. If a map shows a blue patch at the pole, the mind wants it to be a lake. In reality, it may be a thin enrichment spread through regolith, or a few pockets hidden under insulating dust. Second, radar backscatter, which uses radio waves to probe texture and electrical properties rather than brightness. Radar can penetrate the upper regolith and respond to roughness, rock abundance and dielectric constants, which change when materials contain ice. In some contexts, clean water ice can produce distinctive polarization signatures, including a high circular polarization ratio. That signature was used at Mercury to infer polar ice, and Mercury's case became a template for expectation. Mercury is closer to the Sun, yet its polar craters are also permanently shadowed, and radar-bright deposits there match the cold trap story. The comparison is powerful because it shows that extreme cold can exist even on a world scorched by sunlight. On the Moon, radar is trickier, and the trickiness is not a flaw so much as a warning label. Rough blocky ejecta can mimic ice-like backscatter, and fresh craters can look radar-bright for reasons unrelated to volatiles. Multiple scattering between rocks can boost polarization ratios, producing an ice-like signature without any ice. The nuance is that ice is not the only way to get a strong echo, especially at radar wavelengths comparable to rock size. Surface roughness can raise backscatter, and buried blocks can act like corner reflectors that exaggerate brightness. A radar-bright patch inside a cold trap is suggestive, but it is not a verdict, and careful interpretation becomes essential. Third, infrared signatures and thermal mapping, which translate heat into geography. Instruments can measure surface temperature and infer where cold traps should exist, sometimes down to the scale of individual crater interiors. They can also detect spectral features consistent with surface frost in rare cases, but permanent shadow is a measurement challenge. The signal is weak, and stray light can bounce off nearby illuminated slopes and contaminate the darkness. Instrument noise, calibration drift, and the geometry of viewing angles can dominate when the scene is near black and near cryogenic. Even so, thermal models still matter because they connect geometry to stability in a way that can be tested. If a crater floor stays below the sublimation threshold, it can preserve ice for geological time, acting like a freezer that never cycles. If it warms above it even briefly, ice can migrate, thin, or vanish, and that migration can redistribute volatiles across the pole. Mapping temperature becomes a way of mapping the vault, including its weak points. Fourth, impact plume spectroscopy, which turns the Moon into its own laboratory experiment. If a spacecraft deliberately impacts a shadowed region, the plume can loft buried volatiles into sunlight, where spectrometers can search for water vapor, hydroxyl, and other species. The logic is simple. If you cannot see into the shadow, you excavate and watch what escapes. This method has its own uncertainties, and those uncertainties are part of the scientific story rather than an excuse. Plumes mix target material with impactor material, and the expanding cloud cools rapidly as it rises. Species can recondense quickly, and sunlight can break molecules apart, so timing and geometry matter. Yet a detected water signature in an impact plume is hard to dismiss, because it turns a proxy into a direct chemical observation. It is the difference between inferring hydrogen and actually seeing spectral fingerprints of water-bearing species. Even then, the result must be framed carefully, because concentration and distribution remain open questions. These detection methods converge on a cautious conclusion that is stronger than any single dataset. Hydrogen is enriched near the poles, especially in permanently shadowed regions, and some locations show signals consistent with water ice mixed into regolith. The distribution is patchy, and the form may range from grains to thin coatings, with purity varying from place to place. Now we ask the next question that drives the chapter's stakes, and it is a question with deep historical weight. Where did lunar water come from, and how can we tell, when the surface has been gardened by impacts for eons? Origins matter because they connect the Moon to the early solar system, and because different sources imply different co-trapped volatiles. One origin is comet and asteroid delivery, a process that likely peaked during heavy bombardment and then continued at a lower rate. Impacts can deliver water and organics, especially from carbonaceous bodies rich in hydrated minerals and complex carbon. Some fraction is lost to space during impact heating, but some fraction can stick to cold surfaces and migrate to cold traps. Over time, repeated deliveries can accumulate, even if each individual event is inefficient. A single comet may be dramatic, but micrometeorites are relentless, and the Moon has had billions of years to integrate small inputs. The question becomes not whether delivery happened, but how much survived and where it ended up. Another origin is solar wind implantation, which is quiet, global, and easy to underestimate. The sun constantly streams protons outward, and the moon's surface sits exposed without a protective atmosphere. When those protons hit oxygen-bearing minerals, they can form hydroxyl and water-like species in grain rims, creating a thin chemical veneer. This process is global, but cold traps can act as sinks, collecting molecules that hop across the surface. Thermal cycling can release weakly bound species, and micrometeorite impacts can liberate them again, allowing migration in a slow, random walk. Over long times, a molecule formed at mid-latitudes can end in a polar shadow, simply because the shadow is the lowest energy destination. A third origin is outgassing from the lunar interior, which complicates the old picture of a completely dry moon. The moon is not dead in a simple sense, and its volcanic history includes episodes that resurfaced regions and vented gases. Volcanic eruptions and degassing events in the past could have released water, sulfur species, and other volatiles, and even small releases integrated over time could contribute to polar inventories. The modern scientific shift toward a wetter moon did not happen overnight, and it is worth remembering why. For decades, Apollo samples seemed to imply extreme dryness, and the moon was treated as a depleted, airless remnant. Later reanalyses, improved instruments, and new orbital data complicated that certainty, showing that earlier conclusions were partly limited by what could be measured. Isotopes are the key discriminator, at least in principle, because they carry a fingerprint of origin. Deuterium to hydrogen ratios can distinguish comet-like water from solar wind contributions, and oxygen isotopes can add constraints when interpreted with care. Noble gas isotopes trapped with ice can hint at source reservoirs and exposure histories, like tiny time-stamped messages in a frozen archive. But isotopes require samples, and samples are scarce, especially from the places that matter most. Remote sensing can suggest but not fully separate these origins, because mixtures can mimic each other when averaged over large footprints. A far-side polar sample return would be a decisive step, because it would reduce the undersampling loophole that has haunted earlier chapters. The far side's asymmetry returns here in a new form, and it is not just about what we see from Earth. Earlier we asked why the far side is thicker crusted and Maria poor, and now we ask how that history affects volatile retention and access. A higher, older highland terrain changes slopes, illumination, and regolith properties, and those changes shape where cold traps form and how stable they remain. It also changes the engineering of reaching cold traps, and engineering shapes what data gets collected. A mission design that avoids steep terrain may avoid the coldest shadows, and a lander that needs sunlight may target rims rather than floors. When the easiest places to visit are not the most informative, uncertainty lingers longer, and suspicion has room to breathe. Even the definition of ice needs discipline, because the word invites a simple picture that may be wrong. Some hydrogen may be in hydrated minerals, not free ice, and some may be in amorphous frost coatings that come and go with microillumination. Some may be in buried layers protected by insulating regolith, and the resource value depends on concentration, depth, and extractability. So we shift from detection to consequence. Why does ice matter enough to transform the far side from curiosity to strategic destination, even if the deposits are patchy and mixed? The answer is that water is not one commodity but several, and each one changes mission math. First, life support, which is the most direct and the most human reason. Water is drinking water, hygiene water, and oxygen when split, and it is also a buffer against system failure. It reduces the mass that must be launched from Earth, which is the central economic constraint of spaceflight, because launch mass drives cost and architecture. Every kilogram not launched becomes margin for science, shielding, or propulsion, and margins are what make missions robust. If crews can rely on local water, they can extend stays, increase redundancy, and take more ambitious risks. The far side stops being a brief visit and becomes a place where time can be spent. Second, radiation shielding, which is less cinematic but more decisive for survival. Water is rich in hydrogen, and hydrogen is effective at slowing energetic particles through collisions that drain their energy. A habitat surrounded by water or ice-derived material can reduce dose from solar storms and cosmic rays, and that reduction matters over months and years. Shielding is not optional for long stays, and lunar regolith alone has trade-offs in dust, handling, and construction complexity. Water can be stored in tanks, embedded in walls, or used as feedstock for plastics and other hydrogen-rich materials. In a landscape of vacuum and radiation, simple chemistry becomes architecture. Third, propellant production, which turns water into movement and movement into strategy. Electrolysis can split water into hydrogen and oxygen is the dominant mass fraction in many propellant combinations. Oxygen is expensive to lift from Earth, so producing it locally can change mission architectures even if hydrogen remains limited. Hydrogen can be stored, liquefied, or combined with oxygen in high-performance engines. Though storage is challenging in the lunar environment, even partial propellant production can support lander refueling, surface hoppers, and depot concepts in lunar orbit. The point is not a single engine, but a new logistics loop. Propellant changes the map of the solar system, because it changes what counts as far. If you can refuel off Earth, deep space missions become less constrained by launch mass, and trajectories open that would otherwise be impractical. A lunar propellant depot can support transfers to Mars, asteroids and beyond, and the Moon becomes infrastructure rather than a destination. This is where the far side special value compounds and the camera can linger on the limb as Earth disappears from view. The far side offers radio quiet for cosmology and a shield from Earth's interference, which is why it is often described as a natural observatory site. If it also offers usable water at or near the poles, it becomes a place where science and industry overlap, and overlap attracts investment. Investment attracts competition, and competition changes how information is handled, even when everyone insists they are being open. Data that is merely preliminary can become sensitive when it implies advantage. A map of hydrogen becomes, in the wrong context, a map of leverage. Yet the far side adds a constraint that never goes away, and it is as practical as it is political. Communications require relays, because direct line of sight to Earth is blocked, and relays create choke points. A far-side polar operation would depend on orbital infrastructure for command and data return, and that dependence can be framed as vulnerability or as control. Depending on who owns the relay, the same architecture can look like cooperation or gatekeeping. Who schedules bandwidth? Who sets encryption standards? Who decides what telemetry is public and when? When the only bridge across the horizon is technical, the technical becomes geopolitical. So the resource story becomes a governance story, and governance is where suspicion thrives. Who gets to extract, and under what rules, when the environment is shared and the incentives are sharp. The Outer Space Treaty forbids national appropriation, but it leaves room for resource utilization frameworks, and that grey space is where arguments concentrate. National laws and bilateral accords attempt to define safety zones and operational deconfliction, which can be reasonable in engineering terms. Critics see those zones as de facto claims, because exclusion can look like ownership when the terrain is scarce. On the far side, where observation is harder, the same actions can look more secretive than they are. The far side intensifies the argument because it is already psychologically hidden, and psychology matters in public narratives. If a nation mines ice in a crater no one can see from Earth, suspicion comes easily, even if the operation is mundane. If data is released slowly, suspicion hardens, and the cover-up narrative does not need aliens. It only needs scarcity, secrecy habits, and strategic advantage, which are common ingredients in human history. The Moon becomes a mirror, reflecting how societies behave when resources are valuable and oversight is difficult. The mystery is not what physics hides, but what institutions choose to reveal. We should state what the evidence does and does not support, because clarity is the antidote to myth. Evidence supports cold traps, hydrogen enrichment, and plausible water ice in permanently shadowed regions. Evidence does not yet fully quantify accessible reserves at industrial scales, and it does not yet settle origins without samples. Evidence does not justify claims of deliberate concealment, but it does explain why institutions manage information carefully, especially when missions are expensive and reputations are at stake. Science moves by uncertainty budgets, not by declarations, and uncertainty can look like evasion to an audience trained on certainty. The question is whether we can make uncertainty legible without making it suspicious. The scientific stakes remain high even without industry, because polar ice is a time capsule of solar system delivery. It may preserve organics, sulfur compounds, and noble gases that record impact histories, and it may preserve isotopic ratios that constrain when water arrived and how it migrated. In that sense, polar ice is a geological archive, like the far side's craters, but colder and chemically richer. The engineering stakes are equally high, and the visuals here are stark and unforgiving. Working in permanent shadow demands power without sunlight, likely nuclear or beamed energy, and it demands thermal control in extreme cold. Mobility must handle slopes with uncertain regolith strength, and excavation tools must cope with icy soil that can clump, cement, or fracture differently than dry dust. Those constraints shape what can be verified, and when, because some measurements are easy while others are brutally hard. A mission might map hydrogen for years before drilling once, because drilling requires mass, power, and contamination control. A mission might drill but retrieve ambiguous mixtures of ice and hydrated minerals, and each ambiguity can be spun into a story unless methods are public, so transparency becomes a strategic choice, not a public relations gesture, and it must be operational rather than rhetorical. Release raw neutron and radar data sets with processing steps so independent teams can test assumptions. Publish thermal models with assumptions and error bars, and share drill telemetry, sample handling logs, and contamination controls. Make it harder for gaps to become myths, and harder for ordinary uncertainty to be mistaken for deliberate omission. When the public sees how conclusions are built, the mystery shifts from suspicion to curiosity. That shift matters because the far side already carries a cultural weight of hiddenness. Now we connect back to the documentary's central question, which has been orbiting the far side like a silent satellite. What is actually on the far side, and why does it feel like a cover-up, even when the data is public? The answer here is that the most compelling hidden thing is not a structure but a resource that hides because the sun never reaches it. The far side's difference is still geological, still tied to crust, heat, and ancient impacts, and those earlier chapters still stand. But the far side's future may be decided by shadows at the poles, where physics creates scarcity and scarcity creates strategy. Those shadows are where the moon stops being only a record of origins and becomes a node in human logistics. This is the pivot toward the climax. If the far side offers both scientific silence and usable water, then access becomes power, and power invites secrecy even when no grand conspiracy exists. The cover-up narrative evolves from monsters to contracts, from artifacts to infrastructure, and from imagined signals to real supply chains. Next, we follow how nations and agencies respond when the moon becomes economically legible and when maps start to look like balance sheets. We track the emerging rules, the competing architectures, and the first steps toward extracting what has been frozen in shadow for eons. In the end, the question may not be what is hidden, but what we choose to do with what we find. The phrase history's biggest cover-up survives because the far side still feels unreachable, and in that distance the imagination finds room to work. We never see it from Earth, and we meet it through relays, processing, and delay. On screen, the moon turns slowly, half lit, half hidden, while a thin line traces an orbit that vanishes behind the limb. If there were a single hidden truth on the far side, a cover-up would need scale, discipline, and a kind of institutional perfection. It would require consistent suppression across agencies, contractors, nations, and decades, without a single durable leak. That means not just hiding a photograph, but controlling logs, telemetry, budgets, procurement trails, and the quiet conversations where engineers usually brag. It would also require controlling independent observation, which is harder than it sounds once you leave the realm of cinematic secrecy. Amateur tracking, radar ranging, open orbital mechanics, and global telescope networks can verify where spacecraft go. Even when payload details are classified, the basics of motion are public physics, periods, eclipses, and line-of-sight constraints that anyone can compute. Science also resists long-term silence through publishing norms and replication pressure, because careers are built on being first and being right. Teams compete for priority, journals demand methods, and rival groups reprocess the same public datasets. If an anomaly were real and repeatable, it would show up as a residual in someone else's model, and then the race would begin. A real cover-up would have to survive political turnover and budget fights, which are rarely gentle to secrets. It would have to outlast reforms, whistleblowers, and the simple human urge to claim credit. The longer the timeline, the more people touch the system, controllers, archivists, graduate students, and the more fragile the silence becomes. So the first question is not what could be hidden, but what can be delayed, blurred, or reframed without breaking the machinery. Space programs do not run on perfect openness, yet they rarely run on perfect secrecy. Most of what looks like suppression is actually friction, technical, bureaucratic, and sometimes psychological. Secrecy in spaceflight is usually layered, procedural, and selective, like shutters that close only over certain windows. Some layers protect national security, some protect commercial advantage, and some protect a mission from its own early mistakes. In practice, the public sees a polished narrative while the internal record remains messy, iterative, and full of dead ends. Classification is the hardest wall, and it usually targets capabilities rather than discoveries, because capabilities can be reused on Earth. Guidance accuracy, encryption, antenna patterns, sensor performance, and ground network details can be restricted. A single number, like pointing stability or downlink margin, can reveal what else a system might do, and that is why those numbers disappear. Dual-use technology makes the boundary blur, especially during geopolitical tension, when suspicion becomes its own fuel. A camera that maps craters can also map Earth, and a relay architecture can also support military communications. Historically, lunar missions have lived in that shadow, from Cold War tracking networks to modern debates over cislunar surveillance. Proprietary data windows are softer walls, and they are common in planetary science where instruments need time to become trustworthy. Instrument teams often get months to validate calibrations and publish first, before full public release. That delay is not a conspiracy, but it can look like one when spectacular images arrive without the underlying error bars. Public relations adds a third filter that is not secret, yet it feels like one when you only see the highlight reel. Agencies select images that tell a clean story, because messy data undermines confidence and funding. The camera lingers on a perfect crater at sunrise, while the frames with motion blur, dust streaks, or saturated pixels stay off stage. Mission failures add a fourth kind of opacity that is rarely explained well, partly because failure has its own legal and political gravity. A far-side failure can be silent, because the moon blocks direct contact and the relay may not hear. In the control room, silence is not dramatic. It is a flat line, a missing carrier, and a clock that keeps moving. Even a successful mission produces gaps that look suspicious from the outside, because space is an environment of rationing. Bandwidth limits force triage, thumbnails arrive first, and full-resolution products arrive after checks. When a downlink window closes, the rest of the story waits in solid-state memory, sometimes for days. Calibration delays are another ordinary cause of mystery, and they are more technical than most viewers expect. Detectors drift with temperature and radiation, and raw frames can contain artifacts that vanish after correction. Dark current, flat fields, stray light, and compression blocks can all masquerade as features until the pipeline removes them. Geolocation is slower than the public expects, especially for rover data where every meter matters. A spectrum without precise position is a rumour, and position reconstruction can take months. Teams stitch inertial measurements to orbital maps, then reconcile them with landmarks, because one misregistered pixel can invent a discovery. These delays create a vacuum, and the vacuum invites narrative, because the human brain hates unfinished patterns. The far side becomes a screen where uncertainty is mistaken for intent. In the absence of context, a missing dataset feels like a missing confession. Now we confront the claims that keep the cover-up premise alive. They cluster around structures, towers, artifacts, and signals that supposedly prove non-human presence. The visuals often follow a familiar rhythm: zoom in, sharpen, circle a shape, until the circle becomes the argument. Most structure claims begin with a low-resolution image and a strong expectation, which is a powerful combination. A pixelated ridge becomes a wall, a crater rim becomes a dome, and shadows become edges. The mind completes the rest, the way it sees faces in clouds, except here the cloud is a cratered plane. Image geometry is the first trap, because the moon exaggerates relief in ways that feel architectural. Low sun angles stretch shadows, compress slopes, and turn gentle topography into sharp silhouettes. A boulder field can look like a row of pillars when the light grazes it, and the camera's perspective flattens depth. Resolution is the second trap, because cameras sample the world in squares and then compress those squares for transmission. When features approach the pixel scale, the sensor invents shapes through aliasing and compression. A diagonal ridge becomes a staircase, and a curved rim breaks into segments that resemble straight edges. Processing is the third trap, because contrast enhancement can create false boundaries that read as manufactured seams. Edge sharpening, histogram stretching, and mosaicing seams can mimic straight lines and corners. When adjacent frames are normalized differently, The join line can look like a road, even though it is only a mathematical stitch. Confirmation bias is the fourth trap, and it is the most reliable because it recruits emotion as evidence. Once a viewer labels a shape as artificial, every nearby detail is recruited as supporting evidence. The story becomes self-protecting, because any counterexample is dismissed as part of the cover-up. The antidote is not dismissal, but method, and method is something you can show on screen. Compare multiple images at different sun angles, check the original data product, and test whether the feature persists. If a tower vanishes when the light changes, it was never a tower, it was geometry. When higher resolution imaging revisits famous anomalies, most dissolve into geology, and the dissolving is often more interesting than the myth. Linear features become fault scarps, boulder tracks, or ejecta rays aligned by impact physics. The Moon is a museum of impacts, and impacts draw lines, arcs, and rays with ruthless consistency. Some anomalies persist as real puzzles, but they are not the internet's preferred kind, because they do not resolve into a single reveal. They are questions about composition, layering, and timing, not hidden architecture. A strange spectral signature is not a doorway. It is a clue about minerals, melting, and history. Signals claims follow a similar pattern, with different technical traps that are easier to misunderstand in audio form. The far side is radio quiet relative to Earth, yet it is not silent, and instruments can self-generate noise. A receiver can oscillate, a cable can pick up interference, and a cosmic ray can strike electronics like a microscopic hammer. A transient spike in a spectrum can be solar activity, spacecraft electronics, or processing error, and all three can look identical at first glance. Without raw files and calibration context, a spike becomes a story. The most seductive plots are the ones with no error bars, because they leave no room for doubt. The far side also creates unavoidable blackouts and relay choke points, and those gaps are built into the geometry. Those gaps look like deliberate muting, even when they are simply geometry and scheduling. A relay satellite must see both the lander and Earth, and that line-of-sight triangle collapses as orbits drift. Independent tracking and open ephemerides can confirm when a spacecraft is behind the Moon, and the timing can be checked by anyone with the patience to calculate. The blackout's predictable, and predictability is the opposite of a hidden switch. When the carrier returns exactly as the orbit says it should, the drama is only in our interpretation. So the cover-up question becomes a question about literacy and uncertainty, and about what we expect a space mission to look like. People see a curated image and assume the unseen frames contain the real secret, yet most unseen frames are simply unflattering, uncalibrated or redundant, necessary for science, useless for posters. There is also a deeper reason myths attach to the far side, and it is not only invisibility. The far side is genuinely different, and that difference feels like a clue that someone missed. When a landscape looks unfamiliar, we instinctively ask what happened here, and whether the answer was withheld. The near side is Maria